reality is not as solid as it seems. Beneath the surface of what we call existence lies an intricate and beautiful web of rules. A set of principles so strange and counterintuitive that they defy the very logic we rely on in our everyday lives. Imagine a world where information is not just something we store on hard drives or write in books, but is a fundamental, physical, and a primary building block of reality itself. A world where the basic units of data are not fixed, definite ones and zeros, but are fluid, shimmering, and probabilistic entities, existing in a ghostly superposition of multiple states at once. This is a realm where the very act of observation, of looking at something, changes the nature of what is there. It is a world where two particles, separated by the vast, cold emptiness of galaxies, can be so deeply and mysteriously connected that the actions of one instantly, and without any apparent communication, affect the other. It is a world where a simple measurement can erase a universe of possibilities, collapsing the limitless into the defined, the potential into the actual. This is not the realm of science fiction, of fantasy, or of mystical speculation. This is the world as it is described by our best and most fundamental theory of nature, the theory of quantum mechanics. It is the foundation of the universe itself. For centuries, the clockwork, predictable order of classical physics painted a picture of a reality that was, at its core, understandable and intuitive. But as we have learned to probe deeper into the heart of matter, as our experiments have become more sensitive and our theories more sophisticated, we have found that the smallest scales of nature do not behave as our classical instincts tell us they should. They operate on a different logic, a different set of principles, a set of principles so bizarre that even Albert Einstein, one of the great architects of modern physics, struggled to accept them, famously dismissing one of its key features as spooky action at a distance. What if information is not just an abstract concept that we use to describe the world, but is the very scaffolding upon which reality is built? What if the universe is, in some deep and fundamental sense, a cosmic algorithm, a vast quantum computation that is constantly processing the fabric of existence itself? This is a radical and profound idea, one that is emerging from the confluence of physics, computer science, and information theory. It suggests that the its of the physical world, the particles, the fields, the forces, are all, at their core, manifestations of bits of quantum information. Yet, for all its strangeness and its deep philosophical mystery, the world of quantum information is not just a theoretical curiosity. It is a field that holds the potential to revolutionize our technology, to create new forms of computation, of communication, and of security that were previously unimaginable. It promises to give us unbreakable encryption, to build computers that can solve problems that are intractable for even the most powerful classical supercomputers, to create sensors of unprecedented precision. But could the strange and beautiful rules of quantum information also hold the answers to questions that are even more profound? Could the ultimate nature of reality itself be, at its core, an elaborate and beautiful interplay of quantum codes? Could consciousness, could life, could the very structure of space-time be emergent properties of an underlying informational reality? These are the questions that are driving the next great revolution in our understanding of the cosmos. The deeper we look, the stranger it becomes. The quantum world is a realm where our conventional, classical intuition crumbles into dust. And with it, our understanding of something as seemingly straightforward as information undergoes a profound and radical transformation. In classical physics, information is an abstract and secondary concept. It is something that we use to describe a physical system. It is the bits stored on a hard drive, the words written on a page, the positions and velocities of a set of particles. The information describes the reality, but it is not the reality itself. But in the quantum domain, this clear distinction between the physical system and the information it contains begins to dissolve. Quantum information takes on a physical and even primary identity. This physicality changes the very way we define and process information, endowing it with a strange and powerful set of new properties. Imagine a simple, classical bit of information, like the outcome of a coin flip. It is binary. It can be either heads or tails, a 1 or a 0. But a quantum bit, or qubit, the fundamental unit of quantum information, is not so constrained. Thanks to the principle of superposition, a qubit can be a 0, a 1, or, most remarkably, a ghostly, probabilistic blend of both at the same time. It is like a coin that is not heads or tails, but is spinning forever in a shimmering blur of both possibilities, until the moment it is measured. This non-binary nature of the qubit, its ability to exist in a continuous spectrum of states, adds an incredible complexity and power to the very notion of information. It means that a quantum system can store and process a vastly greater amount of information than its classical counterpart. This is not just a quantitative difference, it is a qualitative one. Quantum mechanics challenges the very deterministic perspective that underpins classical physics. A classical system, like a set of billiard balls on a table, is predictable. If you know the initial positions and velocities of all the balls, you can, in principle, calculate their entire future trajectory with perfect accuracy. But a quantum system is fundamentally, irreducibly probabilistic. You can never know its future with certainty. You can only know the probabilities of the different possible outcomes. This means that a quantum system is not just a matter of having enough data. It demands a complete reevaluation of how we interact with the universe, of the very nature of knowledge itself. Information, in this quantum picture, is not just a passive record of a pre-existing reality. It is an active, dynamic, and participatory entity, something that is woven into the very fabric of physical law. The theory of quantum mechanics suggests that all physical systems are, at their core, carriers of information. But this is not just descriptive, classical information. Quantum information has a set of strange and unique properties that set it apart. Properties that enable transformations and processes that are simply impossible in the classical world. Take, for a moment, the concept of measurement. What actually happens when we look at a quantum system? This question strikes at the very heart of the measurement problem, one of the most contentious and deeply debated puzzles in all of quantum mechanics. As we have seen before it is observed, a quantum particle exists in a superposition of all its possible states. It is like an unread book, a book that contains every possible story, every possible narrative, all at the same time. The moment we read the book, the moment we make a measurement, we seem to force it to choose a single, definite story. The superposition collapses, and one of the many possibilities becomes the single, actual reality. But does this act of measurement represent the creation of information, or are we merely revealing a piece of a pre-existing, but hidden, reality? The paradox deepens when we consider the nature of quantum states themselves. In the classical world, you can measure a property of a system, like the temperature of a cup of coffee, without fundamentally changing the system itself. But in the quantum world, this is not always the case. There are certain quantum states that cannot be fully known without destroying them. The very act of gaining information about the system can irrevocably alter it. Observation is not a passive act. It has a real physical cost. This forces us to rethink the very concept of truth or fact. Imagine two scientists trying to understand the state of a single electron. One scientist decides to measure its position with great precision. The other decides to measure its momentum. According to the uncertainty principle, they cannot both get a precise answer. The first scientist's measurement of the position makes the electron's momentum fundamentally uncertain. The second scientist's measurement of the momentum makes its position fundamentally uncertain. They are not just getting different, incomplete pieces of a single, objective picture. They are, in a sense, creating two different and mutually exclusive realities through their choice of measurement. The complementary nature of quantum systems, the fact that certain properties exist in a trade-off, ensures that our knowledge of the quantum world is always and fundamentally partial. It is not a limitation of our instruments. It is a built-in feature of reality. From this inherent uncertainty, we move to an even stranger and more profound quantum feature entanglement. When two or more particles become entangled, their individual quantum states are no longer independent. They merge into a single, shared state, a single wave function that describes the entire system, regardless of the distance separating the particles. Einstein, as we know, dismissed this as an eerie coincidence, a spooky action at a distance. But today, we know that entanglement is a real physical phenomenon. It binds particles together like invisible, non-local threads stretching across the vastness of the cosmos. Through this strange connection, one particle seems to know the state of its partner instantly, no matter how far apart they are. The measurement of one immediately influences the state of the other. The implications of this quantum entanglement for the nature of information are profound and revolutionary. It opens the door to technologies that were once the sole domain of science fiction: quantum teleportation, for example, is no longer a fantasy. It is a real, experimentally verified phenomenon. When two particles are entangled, it is possible to teleport the quantum state of a third particle onto one of the entangled pair, a process that effectively transfers the information across space without physically moving any matter. While this process does not allow for faster-than-light travel, the classical information needed to complete the teleportation process must still be sent at or below the speed of light. It is a phenomenon that fundamentally redefines our understanding of how information can be communicated. But the quantum world does not just offer new possibilities for information, it also imposes strict and beautiful new limits. The no-cloning theorem, a fundamental principle of quantum mechanics, states that it is impossible to create an identical, independent copy of an arbitrary, unknown quantum state. You cannot simply photocopy a qubit in the same way you can photocopy a classical bit. This is a profound and important feature of the quantum world. It ensures that quantum information has a kind of privacy and integrity that classical information lacks. It is the physical basis for the security of quantum cryptography. It also tells us something deep about the nature of reality. The universe, it seems, does not allow for perfect replication. Each quantum system is, in a sense, unique and unreproducible. The entangled pairs themselves carry their own unique measure of informational complexity, a quantity known as entanglement entropy. This entropy is a measure of the shared, non-local information between the particles, the degree of their interconnectedness. And it is this entanglement entropy that explains why, despite the seeming magic of teleportation, entanglement cannot be used to send free, unlimited, and faster-than-light classical information. There are deep and beautifully consistent rules that govern the flow of information in the quantum world. Underpinning all of these strange and wonderful principles is the ever-present hum of the uncertainty principle. Heisenberg's revolutionary assertion that not all properties of a particle can be known with perfect precision at the same time. This is not just a limit on our knowledge, it is a fundamental feature of the information content of the universe itself. It places a cap on how much useful, classical information can be extracted from any quantum system at a given time. To encode and retrieve data in the quantum world requires a series of deliberate trade-offs, a kind of delicate balancing act that is dictated by the fundamental, complementary nature of reality. The complementarity principle, the idea that certain properties, like a particle's wave-like and particle-like nature, are mutually exclusive but equally necessary for a complete description, is the ultimate expression of this trade-off. You can ask a wave question, or you can ask a particle question, but you can never ask both at the same time. The information you gain about one aspect of reality necessarily costs you clarity in another. This is a profound departure from the classical worldview, where perfect, complete knowledge seems, at least in principle, to be attainable. In the quantum world, knowledge is inherently and beautifully incomplete. All of this complexity, all of this strangeness raises a deep and compelling question about the ultimate nature of reality. Is the universe at its core an informational entity? What if the physical world is not the fundamental reality, but is an emergent phenomenon, a manifestation of a deeper underlying quantum computation? This is not just an abstract philosophical speculation. It is an idea that is gaining traction in the world of theoretical physics. The process of decoherence, for example, can be seen as a kind of bridge between the quantum and classical worlds of information. Decoherence is the process by which a quantum system, through its unavoidable interaction with its environment, loses its delicate, superpositional, and entangled nature. The quantum information, the qubitness of the system, is not destroyed, but is rapidly spread out and dissipated into the vast number of degrees of freedom of the environment, becoming, for all practical purposes, irretrievable. This process is what explains why we do not see macroscopic objects like cats in a state of superposition. It is what allows the definite, classical world of our experience to emerge from the fuzzy, probabilistic world of the quantum. It is the process by which the strange, ghostly qubits of the quantum realm are effectively converted into the familiar, solid bits of classical information. The idea of quantum information as being primary suggests that our universe might not just obey physical laws. It might embody them as a form of computation. The evolution of the universe, from the Big Bang to the present day, could be seen as a single, vast, and ongoing quantum computation. A process that is constantly processing information and creating new, more complex structures. In this view, particles are not just things, they are carriers of quantum information, data packets that are navigating a vast, cosmic computational architecture. This is a vision that transcends the classical idea of a universe composed of inert matter and forces. It imagines a universe that is, in a very real sense, alive with information. A universe that is constantly thinking, constantly computing its own reality into existence. And this vision has real, practical applications, particularly in the field of cryptography. The very properties of quantum information that make it so strange: superposition, entanglement. The no-cloning theorem are the same properties that make it the basis for a new and revolutionary kind of security: quantum cryptography, and specifically quantum key distribution, is a technology that uses the principles of quantum mechanics to create a provably secure communication channel. By encoding a secret key in the quantum states of single photons and sending them over an optical fiber, two parties can establish a shared, random key that can be used to encrypt and decrypt their messages. The security of this system is guaranteed by the laws of physics. Any attempt by an eavesdropper to measure the photons will inevitably disturb their quantum state, a disturbance that can be immediately detected by the legitimate users. The randomness inherent in quantum measurement also provides a source of true, unpredictable randomness. which is a crucial ingredient for strong encryption protocols. As we look to the future, the development of a quantum internet, a global network that can transmit and process quantum information, could revolutionize not just our security, but our entire information infrastructure. It would be a network that is not just faster or more efficient, but is fundamentally different. A network that is built on the strange and beautiful logic of the quantum world itself. The journey into the heart of quantum information is a journey that is reshaping our deepest understanding of reality. It is a journey that ties together the abstract concepts of measurement, uncertainty, and entanglement, and reimagines them as the constituent parts of a single, unified, informational framework. And it is a framework that does not just describe reality, it actively determines it. From the security of our most sensitive communications to the most profound and existential questions about the nature of the cosmos. Quantum information is shifting our perspective in deep and powerful ways. Could this be the true foundation of reality? Or is it merely a window into an even deeper, more mysterious layer of existence that is still awaiting our discovery? The tantalizing potential of this new science ensures one thing: this quantum narrative is far, far from over. From the relentless march of entropy and thermodynamics to the deepest and most profound mysteries of quantum mechanics, the concept of information serves as a crucial unifying thread, weaving its way through the vast and varied phenomena that define our physical world. To truly understand how profound and fundamental this concept is, we must first consider the intimate and beautiful relationship between information and entropy, a relationship that is at the very heart of the second law of thermodynamics. We see the effects of this law everywhere: the gradual crumbling of a mountain, the slow fading of a cherished memory, the inevitable cooling of a cup of coffee. Entropy is the universe's great, inexorable tendency towards disorder, towards a state of greater probability and lesser structure. It is the physical basis for the arrow of time. But here is where the story takes a fascinating turn. Information, in its purest, most fundamental sense, is a measure of order, of structure, of reduced uncertainty. When a physical system is in a highly ordered, low-entropy state, like a perfectly arranged deck of cards, we have a great deal of information about it. As the system evolves towards a state of higher entropy, as the cards are shuffled, this information is not destroyed, but is dispersed, becoming harder to access. The act of gaining information about a system, of making a measurement, is an act that can, at least locally, reduce its entropy, an act that brings order out of chaos. This beautiful and intricate dance between the disorder of entropy and the order of information was first given a rigorous mathematical form by the American engineer and mathematician Claude Shannon in his groundbreaking work on information theory in the 1940s. Shannon's work, which was originally designed to understand the limits of communication over noisy channels, provided a precise mathematical definition of information in terms of the reduction of uncertainty, and showed that it was deeply and formally connected to the concept of entropy in thermodynamics. This connection was deepened and made more physical by the work of the physicist Rolf Landauer in the 1960s. Landauer's principle, a cornerstone of the physics of information, established a fundamental link between the abstract, logical operation of computation and the concrete, physical world of energy and heat. Landauer showed that the erasure of a single bit of information from a computational system is not a purely logical act. It has a real physical cost. It must, by necessity, be accompanied by the generation of a small, but unavoidable, amount of heat, an increase in the entropy of the environment. This principle established, once and for all, that computation is not an abstract, disembodied process. It is a physical process, bound by the very same thermodynamic laws that govern the behavior of steam engines and chemical reactions. The metaphysical concept of information was thereby firmly and irrevocably tied to the tangible, material reality of the universe. This intimate relationship between information, entropy, and energy is beautifully illustrated in one of the most famous and enduring thought experiments in the history of physics. Maxwell's demon. In the 19th century, the physicist James Clerk Maxwell imagined a tiny, intelligent being, a demon, who could control a tiny, frictionless door in a partition that divides a box of gas into two chambers. By observing the individual gas molecules, the demon could open the door to let the fast-moving, hot molecules pass into one chamber, and the slow-moving, cold molecules pass into the other. Over time, the demon could create a temperature difference between the two chambers, seemingly decreasing the entropy of the system in violation of the second law of thermodynamics. This paradox puzzled physicists for over a century. The solution, which was finally clarified in the 20th century with the development of information theory, lies in the information processing that the demon must perform. To do its job, the demon must first measure the velocity of each molecule, a process that requires the acquisition of information. It must then store this information in its memory. And finally, it must erase its memory to make room for the next measurement. And it is this act of erasing information that, according to Landauer's principle, must generate entropy, an amount of entropy that is at least as great as the entropy that was seemingly reduced by sorting the molecules. The second law is saved, but at a price. The thought experiment demonstrates, in a beautiful and profound way, how inseparable information is from the physical processes it describes. Information is not a ghostly, non-physical entity. It has a real physical substrate, and its manipulation has real physical consequences. This principle extends to the largest scales of the cosmos. The flow of information in our universe is fundamentally constrained by the laws of relativity. The speed of light is not just the maximum speed at which matter and energy can travel. It is the maximum speed at which information can be transmitted. This cosmic speed limit is what safeguards the principle of causality, the fundamental idea that a cause must always precede its effect. It ensures that the temporal order of events is preserved, that the past cannot be changed by the future. The very structure of space-time, with its fixed and universal speed of light, is a structure that is designed to regulate the flow of information, and it is at the intersection of relativity and information that we find one of the deepest and most challenging puzzles of modern physics. The black hole information paradox. When matter, with all its rich and complex information, falls into a black hole, it seems to be lost to the universe forever, trapped behind the one-way membrane of the event horizon. And when the black hole eventually evaporates through Hawking radiation, that radiation appears to be purely thermal, random, and devoid of any of the information that originally fell in. This would represent a fundamental violation of the quantum mechanical principle that information can never be truly destroyed. The resolution of this paradox is thought to lie in the subtle, quantum correlations and entanglements within the outgoing Hawking radiation, a solution that would require a deep and beautiful synthesis of quantum mechanics, general relativity, and information theory. Beyond the realms of classical physics, thermodynamics, and relativity, the role of information becomes even more central when we consider the dynamic, creative, and evolutionary processes of the universe. Despite the second law's relentless push towards greater disorder, the universe is not a uniform, featureless soup of entropy. On the contrary, it is filled with islands of astonishing and beautiful complexity, the intricate structures of galaxies, the fiery hearts of stars, the delicate and purposeful machinery of living organisms. These ordered structures are not a violation of the second law. They are a consequence of it. They are what the Nobel laureate Ilya Prigogine called dissipative structures. Open systems that maintain their internal order by importing energy from their environment and exporting entropy. A star, for example, is a highly ordered system that maintains its structure by consuming the low-entropy fuel of hydrogen in its core and radiating high-entropy heat and light into the surrounding space. Life is the ultimate example of this process. A living organism is an island of incredible, localized order, a system that actively works to maintain its structure and to create new knowledge, all while increasing the overall entropy of the universe around it. The process by which these complex, ordered structures emerge is known as self-organization, and information is the silent guiding architect of this process. The flow of energy through a system is not enough to create complexity. There must also be an informational blueprint, a set of rules or constraints that guides the self-organizing process. In the formation of a snowflake, this blueprint is provided by the crystalline structure of water and the laws of thermodynamics. In the formation of a galaxy, it is provided by the laws of gravity and the initial density fluctuations in the early universe. And in a living organism, it is provided by the rich and unimaginably complex information encoded in the DNA molecule. This can be understood through the statistical interpretation of entropy, first developed by Ludwig Boltzmann. Boltzmann showed that the entropy of a system is related to the number of possible microscopic arrangements of its constituent parts that correspond to the same macroscopic state. A disordered, high-entropy state, like a shuffled deck of cards, is a state that can be realized in a vast number of different ways. An ordered, low-entropy state, like a deck of cards arranged in perfect numerical and suit order, is a state that can be realized in only one way: information. In this picture is what allows a system to find its way to these rare, improbable, and highly ordered states. The information in the DNA molecule, for example, guides the complex process of protein synthesis, ensuring that the right amino acids are assembled in the right order to create the functional machinery of the cell. It is a process that carves out a tiny, highly ordered path through a vast, chaotic landscape of possibility. The arrow of time, then, is a story of two competing tendencies. On the one hand, there is the relentless universal drive towards greater entropy, towards disorder and heat death. But on the other hand, there is the creative, local, and information-driven process of self-organization, a process that builds islands of exquisite and beautiful complexity against this cosmic tide. Life is the most remarkable and poignant expression of this creative countercurrent. It is a process that thrives by absorbing energy and processing information, a process that creates pockets of meaning and purpose in a universe that is, on the whole, becoming more meaningless and purposeless. And at the heart of this creative process lies the mysterious and powerful role of information. The principles of information are not just at play in the grand cosmic drama of stellar and biological evolution. They are also at the heart of the strange and beautiful world of quantum mechanics, at the smallest scales of reality. The very act of gaining information about a system, the act of measurement, is a process that fundamentally changes the state of that system. This is the basis of the thermodynamics of measurement, a field that explores the deep and intimate connection between information, entropy, and the quantum world. When we measure a property of a quantum particle, like its spin or its position, we are extracting information from it. But this is not a passive act. The measurement process itself is an irreversible, entropy-increasing interaction. It is the process by which the ghostly, probabilistic world of quantum superposition is collapsed into the definite, singular reality of our classical experience. The process of decoherence is the mechanism by which this happens. A quantum system is never truly isolated. It is always interacting, however subtly, with its environment, the information about its delicate superpositional state leaks out into the vast number of degrees of freedom of the surrounding world, becoming, for all practical purposes, irretrievably lost. This is what gives the quantum world its classical appearance. The definite, stable reality we perceive is a consequence of the constant entropic loss of quantum information into the environment. Perhaps one of the most exciting and forward-looking applications of these ideas is in the field of quantum computation. A classical computer processes information one logical step at a time, but a quantum computer, by harnessing the principle of superposition, can explore a vast number of computational paths simultaneously. This quantum parallelism gives it the potential to solve certain problems, like factoring large numbers or simulating complex quantum systems at a speed that is exponentially faster than any classical machine. This is a technology that could revolutionize science, medicine, and artificial intelligence. And as we look to the future, the frontier of information physics hints at even more radical and profound insights. Some researchers, in their quest for a theory of quantum gravity, have proposed that the very fabric of space-time may be, at its core, an informational construct. The holographic principle, for example, theorizes that all the information contained within a three-dimensional volume of space can be completely described by the information encoded on its two-dimensional boundary, like a hologram. If this is true, it would mean that information is not just a property of reality. It may be the very substance of reality itself. Furthermore, a deeper understanding of the thermodynamics of information could lead to a new generation of hyper-efficient technologies. By leveraging principles like Landauer's limit, we might one day be able to build computational and communication systems that operate at the absolute physical limits of energy efficiency. A future where our technological progress is guided not by the raw consumption of energy, but by the subtle and intelligent manipulation of information. And so, as our journey through the world of information comes to a close, we are left with a profound and tantalizing question. What if the universe itself is, at its most fundamental level, a vast, interconnected, and self-organizing field of information? If so, then every star, every planet, every living being would be a constituent part of a grand cosmic informational matrix, a matrix that is constantly evolving, constantly learning, constantly creating new forms of order and complexity. Understanding this deeper, informational reality might not just unlock the next technological revolution. It might also reveal our true place in the intricate and beautiful dance of order, chaos, and knowledge. Information, once seen as a mere abstract description of the world, now emerges as the very scaffolding upon which the universe is built. From the inexorable increase of entropy to the creative process of self-organization, from the strange logic of the quantum world to the grand evolution of the cosmos. It is the thread that illuminates our path towards a deeper and more unified understanding of what energy and matter alone could not explain. As we continue to probe the mysteries of information and its physical manifestations, one thing becomes clear: the story of the universe is not just about what it is made of, but about what it communicates. And in learning to read this cosmic message, we are not just deciphering the secrets of the universe. We are, in a very real sense, discovering our own. Life, at its very essence, can be understood as a profoundly sophisticated and ancient information processing system. Every single cell in your body, from the neurons in your brain to the muscle fibers in your heart, operates like a tiny, powerful, and exquisitely designed biological computer, constantly handling a vast and complex flow of information to sustain the miracle of your existence. And the source code for this incredible biological software is not written in silicon, but in the elegant double helix structure of the DNA molecule. DNA is not just a chemical. It is nature's own time-tested programming language, a biological script that has been written, edited, and refined over the course of nearly 4 billion years of evolution. This single, remarkable molecule, present in almost every cell of your body, contains the complete set of instructions, the architectural blueprint, that guides everything from the division of your cells to the synthesis of the proteins that are the workhorses of your biological machinery. It is a vast and ancient library of life, a library where every book is a gene, and every chapter contains a piece of the accumulated evolutionary wisdom of your ancestors. The process of evolution itself can be seen as the ongoing editing and refinement of this great genetic library. Through the random, mutational process of trial and error, life is constantly experimenting with new editions of its own chapters. Random changes in the genetic information, mutations, recombinations, and the more subtle epigenetic modifications that can be influenced by the environment create a constant stream of new variations. Natural selection then acts as a harsh, but ultimately creative, editor. Those variations that happen to provide a survival or reproductive advantage in a particular environment are preserved and passed on to the next generation, while those that do not are discarded. This process, repeated over countless generations, is not just a random walk through the space of possibility. It is a powerful optimization algorithm, a process that allows life to learn, to adapt, and to accumulate an ever-growing repository of knowledge about how to thrive in an often hostile and unpredictable universe. These principles of biological information processing are not just metaphorical. They are deeply and formally connected to the mathematical principles of information theory, a field that was originally developed to understand the transmission of data in man-made communication systems. The rules of information fidelity, of redundancy, of error correction, are just as relevant to the replication of a DNA molecule as they are to the transmission of a digital file over the internet. The genetic code, for example, is brimming with built-in safety mechanisms. It has a degree of redundancy, where multiple different codons can code for the same amino acid, providing a buffer against some mutations. And our cells have evolved a sophisticated and complex machinery of DNA repair enzymes, molecular proofreaders that constantly scan the genome for errors and correct them, ensuring that the vital instructional information is preserved with an incredible degree of fidelity. But this stability does not stifle evolution. On the contrary, it provides the stable, reliable foundation upon which the creative process of variation and selection can occur. The story of life's information processing continues in the intricate, dynamic, and beautiful networks of communication that exist within and between our cells. The flow of information from the genetic archive of the DNA to the functional machinery of the cell is a marvel of molecular engineering. In a process called transcription, a segment of the DNA is copied into a messenger RNA molecule. This mRNA molecule then travels out of the nucleus and into the cytoplasm, where, in a process called translation, its sequence is read by a molecular machine called a ribosome, which assembles a specific protein, amino acid by amino acid, according to the genetic instructions. This is the central dogma of molecular biology, the fundamental flow of information from DNA to RNA to protein. And it is a process that is happening trillions of times a second in your body right now. The way our cells process this vast amount of data is a masterclass in decentralized, distributed computing. There is no central processing unit, no single brain of the cell. Instead, the cell is a complex, self-organizing network of interacting molecules, a symphony of biochemical signals where each part is in constant communication with the whole. allowing the cell to respond and adapt to its constantly changing environment in a remarkably efficient and robust way. The role of information in building the complexity of life becomes even more apparent when we consider the great evolutionary transition from single-celled organisms to multicellular life. This was a leap that required a complete and radical restructuring of how biological information is stored, processed, and transmitted. Multicellular organisms had to invent new ways to coordinate the functions of billions and even trillions of interconnected cells to ensure that they all work together for the good of the whole. The emergence of the nervous system was a key innovation in this process. The neural network of an animal is an advanced biological supercomputer, a system that is dedicated to processing the vast amount of sensory information from the environment, to driving complex behaviors, and to fostering the process of decision-making. But life's ingenuity in information processing is not limited to the top-down control of neural systems. At the other end of the biological spectrum, we find phenomena like horizontal gene transfer in bacteria, a process where single-celled organisms can directly exchange genetic information with each other, even across species boundaries. It is a kind of biological internet, a peer-to-peer network that allows for the rapid spread of useful genetic innovations, like antibiotic resistance, through the microbial world. These different strategies, the centralized processing of a nervous system and the decentralized network of horizontal gene transfer, are both powerful examples of how life, at every scale, is constantly experimenting with new and more efficient ways to handle the challenges of evolutionary adaptation. Adaptation itself, at its very core, is a process of changing how information is processed and utilized. Organisms are not passive slaves to their genetic programming. They are active, learning systems that are constantly adjusting their internal and external information strategies in response to the pressures of their environment. The process of learning and memory, for example, which is so highly developed in species like birds and mammals, is a powerful adaptive mechanism. It allows an organism to store information about its past experiences, the location of a food source, the presence of a predator, and to use that information to make better, more informed decisions in the future. The environment itself acts as a constant stream of feedback, a set of data that shapes and refines these learning processes, forcing life to operate like a complex, adaptive algorithm that is constantly working to maximize its efficiency and its chances of survival. The influence of information becomes even more profound and fascinating when we consider how these evolutionary processes extend beyond the realm of biology and into the realm of culture and cognition. The evolution of language in human beings, for example, was not just the development of a new way to make sounds. It was a revolutionary leap in the technology of information storage and transmission. Language allowed knowledge to be accumulated, shared, and built upon across generations. A process that is far more rapid and powerful than the slow generational transfer of genetic information. Language is, in a very real sense, a form of externalized biological information, a mimetic code that has allowed human culture to evolve and adapt at a breathtaking pace. And over the course of our history, we have continued to extend the principles of biological information processing into our artificial systems, from the invention of writing and the printing press to the development of the digital, computational marvels that define our modern world. Even the nature of intelligence itself is deeply and inextricably tied to the way that organisms process and utilize information. The increased complexity of the neural connections in the brains of so-called intelligent species is a direct reflection of the growing need to analyze, to store, and to respond to an ever-increasing amount of data from a complex and ever-changing environment. Human cognition, and by extension, human intelligence, has co-evolved with these powerful information processing abilities. To be intelligent is not just to be able to think, it is to be able to efficiently acquire, to analyze, to synthesize, and to translate information into effective, purposeful action. Understanding these deep and beautiful connections between biology, information theory, and evolution paints a new and compelling portrait of life. It is a narrative of constant change, of relentless refinement, and of beautiful adaptation. A narrative in which information lies at the very heart of everything. Life does not evolve randomly. It evolves systematically, constantly finding new and more ingenious ways to process, to store, and to leverage its vast and growing informational wealth in order to thrive against the odds. The evolutionary journey of life, from the first self-replicating molecule to the complex, global civilization of our own species, is not just a story of the survival of the fittest. It is the story of the survival of the most informationally adept. And as we stand at this unique moment in history, as we begin to create new, artificial forms of intelligence, we are not just continuing this evolutionary process. We are, perhaps, on the verge of accelerating it in ways that are both thrilling and deeply, profoundly unsettling. The story of life is the story of information, and it is a story that is far, far from over. The quantum phenomenon of entanglement is not just a strange and counterintuitive curiosity of the subatomic world. It is an experimentally verified reality, a feature of the cosmos that forces us to fundamentally reevaluate our classical notions of space, of distance, and of connection. It is the discovery that two or more particles can share a single, unified quantum state, a relationship so profound and immediate that it seems to challenge the very locality of reality. The idea that objects can only be influenced by their immediate surroundings. But this is where the story gets even stranger. The concept is so bizarre that it deeply troubled even Albert Einstein, who, along with his colleagues Boris Podolsky and Nathan Rosen, famously labeled it spooky action at a distance. In their 1935 paper, they constructed the EPR paradox, a thought experiment designed to show that the predictions of quantum mechanics were so strange that the theory must be incomplete. They argued that if quantum mechanics was right, then particles could seemingly communicate faster than the speed of light, a clear violation of one of the most fundamental principles of his theory of relativity. For Einstein, this spookiness was a sign that there must be some local hidden variables, some unknown properties that the particles carried with them that were predetermining the outcomes of the measurements, thus preserving the comforting classical notion of locality. For decades, this was a philosophical debate, but in the 1960s, the physicist John Bell, in a stroke of brilliant insight, formulated a mathematical theorem, now known as Bell's theorem, which provided a way to experimentally test the predictions of quantum mechanics against any possible local hidden variable theory. Bell's theorem, and the numerous, increasingly precise Bell test experiments that have been performed in the decades since, have delivered a stunning and unambiguous verdict. The inequalities derived by Bell have been overwhelmingly violated, time and time again, confirming the non-local predictions of quantum mechanics and ruling out the possibility of any local hidden variable explanation. The spooky action is real. The universe is, in some deep and fundamental way, non-local. This does not mean that we can use entanglement to send faster-than-light signals and violate causality. But the underlying instantaneous connection is undeniably there. It tells us that our intuitive picture of a universe made up of separate, independent objects is an illusion. The answer to how this happens lies in the strange nature of quantum measurement. When we observe or measure one of the entangled particles, its wave function, the cloud of its possibilities, collapses and it settles into a definite state. And because the two particles are part of a single, unified quantum system, this collapse is not a local event. The entire entangled wave function collapses at once, and this means that the state of the distant, unmeasured partner is also instantly determined. This phenomenon of wave function collapse raises profound questions about the role of the observer in defining reality. Is the universe fundamentally deterministic, with the collapse just revealing a pre-existing state? Or does the act of observation itself play a creative role in shaping the outcome? This brings us to the concept of decoherence, a process that helps to bridge the gap between the strange, superpositional world of the quantum and the definite, classical world of our experience. Decoherence explains how a quantum system, through its unavoidable entanglement with its environment, rapidly loses its quantum coherence, its ability to be in a superposition of states. The information about the superposition leaks out into the environment, making it practically impossible to observe. This is why we do not see macroscopic objects in a state of superposition. But decoherence does not fully solve the measurement problem, it just pushes it back. Different interpretations of quantum mechanics, from the traditional Copenhagen interpretation to the radical many worlds interpretation, continue to wrestle with this deep, conceptual riddle. The profound implications of quantum entanglement extend far beyond the realm of theoretical physics and into the world of revolutionary new technologies. The strange, non-local connection between entangled particles is not just a philosophical puzzle. It is a powerful new resource that we are just beginning to learn how to harness. Take, for example, the field of quantum cryptography. The security of our current classical communication systems is based on the computational difficulty of solving certain mathematical problems, like factoring large numbers. But a sufficiently powerful quantum computer could, in principle, solve these problems easily, rendering much of our current encryption obsolete. Quantum cryptography offers a new and fundamentally more secure paradigm. By using entangled photons to create a secret, shared key between two parties, a process known as quantum key distribution, it is possible to create a communication channel whose security is guaranteed not by computational complexity, but by the fundamental laws of physics. Any attempt by an eavesdropper to intercept and measure the photons will inevitably disturb their entangled state, a disturbance that can be immediately detected by the legitimate users. It is a system that is, in principle, unhackable. Similarly, the phenomenon of quantum teleportation, once the stuff of science fiction, is now a routine, if still small-scale, laboratory experiment. It uses the principles of entanglement to transfer the complete quantum state of a particle from one location to another, without physically moving the particle itself. This is not the beaming up of Captain Kirk, but it is a revolutionary new way to think about the transmission of information, a process that could one day be the foundation of a quantum internet, a global network that can transmit and process quantum information. And it is in the field of quantum computing that the power of entanglement is most fully realized. A classical computer processes bits of information that are either a 0 or a 1. A quantum computer uses qubits, which can be in a superposition of both. But the true power of a quantum computer comes from its ability to entangle these qubits. By entangling a large number of qubits, a quantum computer can create a vast, multidimensional computational space, allowing it to explore an astronomical number of possibilities simultaneously. This quantum parallelism is what gives a quantum computer the potential to solve certain problems, from designing new drugs and materials to breaking complex codes at a speed that is exponentially faster than any classical machine. The strange, non-local bond of entanglement is what allows the qubits to work together in a coherent, powerful harmony, unlocking a level of computational power that was previously unimaginable. But what if the significance of entanglement extends even beyond the realms of technology and into the very fabric of space-time itself? Some of the most exciting and speculative ideas in modern theoretical physics suggest that entanglement may not just be a phenomenon that happens in space-time, it may be the very thing that creates space-time. The ER equals EPR conjecture, proposed by the physicists Juan Maldacena and Leonard Susskind, is one of the most provocative of these ideas. It suggests a deep and surprising equivalence between two seemingly disparate concepts, quantum entanglement and wormholes. The conjecture posits that when two particles are quantum mechanically entangled, they are, in a sense, connected by a microscopic wormhole. This is a staggering idea. It suggests that the strange, non-local connection of entanglement is actually a manifestation of a deeper, geometrical connection in a higher dimensional space. It implies that the geometry of space-time is not a fundamental, pre-existing background, but is an emergent phenomenon, something that is woven from the intricate and complex web of quantum entanglements between the fundamental constituents of the universe. In this view, space is not the thing that separates us. It is the thing that connects us. A vast network of quantum threads, this idea, while still highly theoretical, provides a powerful and beautiful new lens through which to view the universe. It offers a potential path towards a theory of quantum gravity, a theory that can unify the two great pillars of modern physics. It suggests that the deep puzzles of quantum mechanics and the deep puzzles of general relativity may be two sides of the same informational coin, and it has profound philosophical implications. If the fabric of reality is woven from the threads of entanglement, then the universe is not a collection of separate, independent objects, but a single, holistic, and deeply interconnected whole. This is a worldview that resonates with the deepest intuitions of many spiritual and contemplative traditions. The idea that we are all one is not just a poetic sentiment. It may be a deep, physical truth, a truth that is written in the non-local, entangled language of the cosmos itself. The implications of this for our own human experience are vast and largely unexplored. If our own consciousness is, as some have speculated, a quantum phenomenon, then we too may be part of this universal entangled web. The feelings of empathy, of connection, of collective consciousness may not be just psychological phenomena, but may have a real, physical basis in the entangled nature of our own being. Imagine a future where entanglement is not just a topic for the laboratory, but a practical and integrated part of our everyday lives. Our most sensitive data is transmitted with perfect security through quantum encrypted networks. Quantum computers are solving some of humanity's most pressing problems, from climate change to disease, and perhaps even our understanding of ourselves, of our own interconnectedness, will have been transformed by this deep quantum insight, for all its promise. Entanglement reminds us that the universe retains its deep and beautiful mysteries. It challenges our most basic intuitions about causality, about distance, about reality itself. It urges us to rethink our place in a cosmos where the boundaries between here and there, between now and then, between self and other, may be far more fluid and far more mysterious than we ever imagined. What we have uncovered so far is merely the tip of a vast and magnificent iceberg. And with each new experiment, with each new theoretical insight, the strange and beautiful world of quantum entanglement continues to provoke, to puzzle, and to inspire. It is an invitation, not just to scientists, but to all of us, to look closer, to think deeper, and to imagine a universe that is far more interconnected and far more wonderful than it first appears. The universe is a sprawling and often bewildering enigma, a puzzle that has captivated the greatest minds of humanity for centuries. We have observed its patterns, we have dissected its laws, and we have spun beautiful, intricate theories about its origins and its destiny. But what if we were to tell you that the very fabric of reality itself could be understood in a radically new and powerful way? What if the universe, in all its vastness and complexity, operates not like a grand clockwork machine, but like a colossal and unimaginably powerful quantum computer? This is a paradigm-shifting idea, one that is emerging from the frontiers of theoretical physics and computer science. It is a vision that reframes our understanding of reality, suggesting that at its most fundamental level, the cosmos may not be made of matter and energy, but of information, and that the laws of physics are not just a set of static rules, but are a form of ongoing, dynamic computation. This concept of a computational universe blurs the line between the observer and the observed, between the physical and the informational, in a way that is both deeply challenging and profoundly beautiful. At the heart of this new paradigm lies a radical reinterpretation of the laws of physics themselves. The equations and the constants that we have so carefully mapped, from the elegant mechanics of Newton to the curved space-time of Einstein and the probabilistic waves of quantum mechanics, may be better understood not as a description of reality, but as the operating system for reality. They are the rules, the algorithms, that govern how the state of the universe is processed and evolved from one moment to the next. Quantum mechanics, in this picture, becomes the fundamental programming language of the cosmos. It is a language that is not deterministic, but probabilistic. It does not deal in absolute certainties, but in a rich and complex landscape of possibilities. The wave function of a quantum system is not just a mathematical tool, it is a complete, informational description of that system, a catalog of all its potential states. And the process of measurement, the infamous collapse of the wave function, is a computational step, a moment when the vast, superpositional potential is processed and a single, definite output is rendered into our classical reality. The ongoing mathematical dance of quantum mechanics is what gives the universe its structure, its texture, and its very existence. Look deeper into this computational cosmos, and you will find the principle of quantum superposition, the astounding ability of a particle to exist in multiple states simultaneously. If you have heard of Schrödinger's cat with its ghostly existence between life and death, you have already grasped the central paradox of this concept. But on a computational level, superposition is not a paradox. It is a resource. It is the basis for a massive and natural form of parallel processing. A classical computer must handle a computation one step at a time in a linear sequence. But a quantum system, by virtue of its ability to exist in a superposition of all possible states, can explore a vast number of computational paths all at once. This opens up a breathtaking possibility. What if the universe itself is performing a kind of continuous, massive parallel computation? What if every quantum event, every collapse of a wave function, is a moment of information processing, creating ripples of newly computed reality that propagate through the cosmos? This would suggest that the universe has an inherent and almost unimaginable computational efficiency, a power that is far beyond anything we could ever hope to achieve with our own man-made technologies. Central to this model of a computational universe is the role of measurement. As we have seen, a quantum system exists as a cloud of possibilities until an observation forces it to collapse into a single, definitive state. In the same way, a computation is not just a sequence of potential solutions. It must, at some point, result in a definite output. The observer in this picture is not just a passive element of reality. They are an active and perhaps even necessary participant. Every time we make a measurement, every time we interact with the world in a way that resolves a quantum uncertainty, we are, in a sense, contributing to the ongoing computation of the universe's state. We are not just reading the cosmic code, we are helping to write it. But what happens when errors arise in this incredible cosmic system? Just as our own computers are prone to glitches and bugs, the universe is not immune to the disruptive influence of quantum noise and decoherence. Decoherence is the process by which a quantum system, through its unavoidable interaction with its environment, loses its delicate, superpositional nature. It is the process by which the strange, ghostly qubits of the quantum realm are effectively converted into the familiar, solid bits of classical information. This could be seen as a form of error. But what if the universe has a built-in mechanism for quantum error correction? This is a concept that is at the very forefront of the development of real-world quantum computers. The idea of encoding quantum information in a redundant way, so that it can be protected from the effects of decoherence. Could it be that the universe itself employs a form of natural quantum error correction? Could the remarkable stability and consistency of our physical laws be a consequence of an inherent informational redundancy in the fabric of reality? A system that is constantly correcting errors as they arise and preserving the deep computational integrity of existence. The computational nature of the universe is also reflected in the strange, non-local structure of quantum causality. In our classical world, cause and effect follow a clear linear chain of events. But in the quantum realm, as we have seen with entanglement, the relationships between events can be far more subtle and interconnected. Entanglement creates a form of spooky, non-local connection between particles that defies our classical intuition about space and distance. If we translate this into a computational model of the universe, it suggests that the flow of information may not be a simple, linear process. It may follow the intricate, entangled pathways of the quantum world. The processing of reality is not a straight line, but a complex, interconnected web, a graph of relational information where the state of one part can instantly influence the state of another, no matter how far apart they are. This leads to an even more radical idea. What if space-time itself is not a fundamental, pre-existing background, but is an emergent phenomenon, something that is born from the processing of quantum information? Some of the most advanced theories of quantum gravity, like the holographic principle, suggest that the three-dimensional space we experience may be a projection, a hologram that is encoded on a two-dimensional informational surface at the boundary of our universe. In this view, the very fabric of space-time is woven from the threads of quantum entanglement, the geometry of space, the flow of time, the force of gravity. All of these could be emergent properties of a deeper, underlying quantum computation. We can see hints of this computational logic even in the processes of the natural world. Quantum algorithms, like Shor's algorithm for factoring numbers or Grover's algorithm for searching a database, are specific, highly efficient solutions that are optimized for quantum systems. And intriguingly, some of these quantum computational strategies share deep structural parallels with natural processes, from the way that plants perform photosynthesis to the way that birds navigate using the Earth's magnetic field. It is as if nature itself has, over billions of years of evolution, discovered and implemented some of the most efficient quantum algorithms. This brings us to the most tantalizing and most speculative hypothesis of all. If the universe is indeed a quantum computer, could reality itself be an intricately coded simulation? The simulation hypothesis. The idea that our entire existence might be a program running on a vast cosmic computer is one that has long been a staple of science fiction, but it is now being seriously considered by some physicists and philosophers. If this were true, it would provide a natural explanation for some of the strange, built-in limits of our universe, like the speed of light or the Planck length. These would not be arbitrary constants, but would be the processing speed and the pixel size of the underlying computational reality. The view of the universe as a quantum computational system does not just reframe our understanding of the physical world. It opens up vast, new frontiers for exploration. It forces us to reconsider age-old philosophical questions in the new and powerful light of physics and computer science. If the universe is computing reality, then to understand that computation would be to understand the ultimate nature of existence, and perhaps it would grant us an unprecedented ability to interact with and to shape that reality, to move from being just a variable in the cosmic algorithm to becoming one of its programmers. This perspective does not reduce the awe and wonder of existence. It enhances it. It imagines a cosmos that is alive with a ceaseless and almost unimaginably complex process of calculation. A universe that is mathematically encoding and processing every atom, every star, every galaxy. And it is a reality in which you, the conscious observer, are a crucial and integral participant, not a passive recipient of information, but a node in the network, influencing the system and being influenced by it, connected through the invisible, entangled threads of quantum information to every other part of this incredible, unending equation. Imagine for a moment that this vast, three-dimensional universe, with all its depth, its substance, its seemingly solid reality, is not as it seems. What if everything we experience, the space that separates us, the time that flows around us, the very matter that makes up our bodies, is an elaborate and beautiful projection, a cosmic hologram? What if our entire, rich, three-dimensional world is, in fact, a higher-dimensional mirage? Its information compressed and encoded onto a simpler, two-dimensional canvas at the very edge of our cosmos. This startling and deeply counterintuitive idea is at the heart of what physicists call the holographic principle. And it is a concept that challenges the very fabric of reality as we know it, suggesting a universe that is fundamentally informational, a universe where the distinction between the container and the contained, between the boundary and the bulk, is not as clear as we once thought. The origins of this revolutionary idea lie in one of the most unlikely and most mysterious corners of the cosmos, the study of black holes. For decades, black holes were seen as the ultimate information destroyers. Their immense gravity creates an event horizon, a one-way membrane from which nothing, not even light, can escape. Any information that falls into a black hole seems to be lost to the universe forever, a direct violation of the fundamental quantum mechanical principle that information can never be truly destroyed. In the 1970s, the physicist Jacob Bekenstein, and later Stephen Hawking, discovered something remarkable. They found that the entropy of a black hole, a measure of its information content, is not proportional to its three-dimensional volume, as one would expect, but is proportional to the two-dimensional area of its event horizon. It is as if all the information about the three-dimensional objects that have fallen into the black hole is somehow stored or encoded on its two-dimensional surface. This was the first hint of the holographic principle. It was a suggestion that the information content of a region of space is not as extensive as it seems, that it can be fully described by a theory that lives on its boundary. This idea was given a precise mathematical form in the 1990s by the physicist Juan Maldacena in what is now known as the ADI-CFT correspondence. This is a profound and powerful duality, a kind of mathematical Rosetta Stone that shows a precise equivalence between two, seemingly very different, physical theories. On one side of the duality, we have a theory of gravity, like string theory, that lives in a curved, five-dimensional anti-de Sitter space. On the other side, we have a quantum field theory, a conformal field theory that has no gravity and lives on the flat, four-dimensional boundary of that space. The correspondence states that these two theories are completely equivalent. Every question you can ask in the five-dimensional gravitational theory has a corresponding and equally valid question in the four-dimensional quantum field theory on the boundary. This is a stunning and revolutionary idea. It suggests that gravity itself, which we have long considered to be one of the fundamental forces of nature, may not be fundamental at all. It may be an emergent phenomenon, a holographic projection of a deeper, non-gravitational quantum reality that lives on a lower dimensional surface. The three-dimensional world of our experience, with all its gravitational complexity, could be a hologram generated by the quantum interactions of particles on a distant, two-dimensional screen. This holographic vision of the universe has profound implications for our understanding of space and time. If the geometry of space-time is an emergent holographic property, then it may not be a smooth, continuous fabric at its most fundamental level. It may be quantized, made up of discrete, indivisible units, like the pixels on a computer screen. The search for this holographic noise, the subtle quantum graininess of space-time, is an active, if highly challenging, area of experimental physics. High-energy experiments at particle accelerators and precise, astronomical observations of the cosmic microwave background are both searching for the faint, indirect clues that could reveal the pixelated nature of our reality. If the holographic principle holds true, it would also force us to rethink our most basic notions of causality and locality. In a holographic universe, the idea that events are determined by their local causes and effects may no longer be the fundamental story. The unfolding of events in our three-dimensional bulk would be dictated by the complex, non-local quantum correlations and entanglements of the information on the two-dimensional boundary. The universe would be, in a very real sense, a holistic and interconnected system, where the part is always a reflection of the whole. This perspective also offers a new and powerful way to think about the nature of gravity itself. The physicist Eric Verlinde, building on the holographic principle, has proposed that gravity is not a fundamental force, but is an entropic force. It is an emergent phenomenon that arises from the thermodynamic principles of information. In this view, gravity is a consequence of the universe's tendency to maximize its entropy, a statistical force that pulls things together because it is the most probable configuration of the underlying informational degrees of freedom. This is a beautiful and compelling idea, one that connects the geometry of space-time directly to the laws of information and thermodynamics. And the mathematical architecture for exploring these holographic ideas is provided by the powerful framework of quantum field theory, and particularly conformal field theory. These theories describe how the information on a lower dimensional boundary can give rise to the rich and dynamic phenomena of a higher dimensional space. The study of these intricate mathematical mappings is one of the most exciting and productive areas of modern theoretical physics, and it is providing us with new and powerful insights into the deep, and as yet unsolved, challenge of quantum gravity. The holographic principle offers a compelling and beautiful starting point for unifying the two great, and seemingly incompatible, pillars of modern physics, general relativity and quantum mechanics. It suggests that they may be two different, dual descriptions of the same, underlying informational reality. Beyond its revolutionary implications for physics, the idea of a holographic universe raises a host of deep and unsettling philosophical questions. If our familiar three-dimensional world is, in some sense, an illusion, a projection of a more fundamental, two-dimensional reality, then what does this say about the nature of existence itself? Are we, as conscious three-dimensional beings, just complex patterns in a cosmic hologram? What are the ultimate limits of our knowledge, if the reality we are trying to understand is not the fundamental one? These are questions that push the boundaries of science and steer us into the deep, and often murky, waters of metaphysics, of epistemology, and of existentialism The holographic principle is a profound and humbling reminder of the potential limitations of our own evolved cognition. Our senses, our brain, have been shaped by the pressures of natural selection to be effective tools for surviving and reproducing in a three-dimensional macroscopic world. They are not necessarily designed to perceive the ultimate, fundamental nature of reality. The world we experience is a user interface, a simplified, and likely very partial, representation of a much deeper and far stranger underlying reality. But it is this very drive to question, to look beyond the surface, to strive for a deeper understanding, that is the hallmark of our species. The holographic principle also invites us to reconsider our picture of science itself. Science is not a process of uncovering a single, fixed, and absolute truth. It is an evolving narrative, a story that we refine and rewrite with every new discovery. The idea that even our most fundamental concepts, like space and time, could be emergent, and perhaps even illusory, is a powerful testament to the open-ended and self-correcting nature of the scientific process. It teaches us that we must be prepared to question everything, to hold our most cherished theories with a degree of humility, and to be open to the possibility that the next great revolution in our understanding will come from a place we least expect. As we gaze into the deep mysteries of the universe, from the swirling, information-scrambling event horizons of black holes to the subtle, quantum fabric of space-time itself, the holographic principle stands as a beacon of what science can achieve when it dares to challenge its own most fundamental conventions. It is more than just a theory. It is a testament to the boundless creativity and the relentless curiosity of the human mind. And as we continue to explore the implications of this strange and beautiful idea, we are not just decoding the secrets of the cosmos, we are also, in a very real sense, decoding ourselves and our own mysterious and holographic place within the grand and perhaps illusory cosmic drama. The reality we perceive, with its solid objects, its linear flow of time, and its clear causal relationships, is like a beautifully woven and seemingly complete tapestry. But what if, on closer inspection, we find that the threads are not as tightly knit as they appear? What if we discover gaps, tears, and strange, unexplored patterns in this fabric we call existence? The journey into the heart of modern physics is a journey into this very realization. It is the discovery that our classical, common-sense picture of the world is a powerful but ultimately limited approximation of a much deeper, stranger, and more mysterious reality. And it is a journey that leads us to one of the most enigmatic questions of all: can we ever fully and completely decode the true nature of reality? The first and most profound challenge to our classical worldview comes from the quantum realm. The concept of an objective reality, the idea that the world exists with definite properties, independent of our observation of it, seems, at first glance, to be an obvious and necessary starting point for any scientific inquiry. A tree in the forest is a tree, whether we are there to see it or not. But quantum mechanics, with its strange logic of superposition and measurement, complicates this simple picture. The observer effect demonstrates that the very act of measuring a quantum system can alter its state. An electron does not have a definite position until we measure it. Before the measurement, it exists as a wave of probability. Our observation forces this wave to collapse into a single, definite location. It is as though the universe only paints the picture of reality once we decide to look at the canvas. This raises a deep and unsettling question: how much of what we perceive as real is a property of the world itself, and how much is a product of our interaction with it, a reflection of the questions we ask and the measurements we make? This inherent fuzziness of the quantum world is quantified by Heisenberg's uncertainty principle. At the most fundamental level, it is impossible to simultaneously know certain pairs of properties of a particle, like its position and its momentum, with perfect accuracy. The more precisely we know one, the less we can know about the other. This is not a limitation of our instruments. It is an intrinsic, built-in feature of nature. It is as if reality itself has a fundamental blurriness at its core, a limit to its own definiteness. This suggests that our quest for a complete and perfectly precise knowledge of the universe may be, in principle, an impossible one. This fundamental limit on our knowledge is not just a feature of the physical world, it is also a feature of the abstract, mathematical world we use to describe it. In 1931, the logician Kurt Gödel, in one of the most stunning intellectual achievements of the 20th century, proved his incompleteness theorems. These theorems show that in any sufficiently complex and consistent mathematical system, there will always be true statements that cannot be proven. Within the rules of that system, mathematics, the very language of science, the tool we use to build our theories of reality, is itself fundamentally and forever incomplete. This has profound implications. If even the abstract logical framework we use to understand the universe has inherent, unprovable truths, how can we ever hope to build a final, complete theory of everything? Gödel's work suggests that our knowledge will always be a work in progress, a system that can be made more complete only by introducing new and themselves unprovable axioms. The quest for an absolute final foundation for our knowledge is a logical impossibility. This inherent incompleteness of our theoretical frameworks is reflected in the ongoing, and often contentious, debates about the interpretation of quantum mechanics itself, the Copenhagen interpretation, the many worlds interpretation, Bohmian mechanics. Each of these offers a different and seemingly incompatible picture of the underlying reality of the quantum world. Each is a different and partial attempt to make sense of the same strange set of experimental results. The fact that, after a century of debate, there is still no consensus on which, if any, of these interpretations is correct is a powerful testament to the deep, and perhaps irreducible, mystery that lies at the heart of our most fundamental theory. But the limits of our knowledge are not just found in the bizarre world of the quantum or the abstract realm of mathematics. We also encounter them when we try to bridge the gap between the simple and the complex, between the microscopic and the macroscopic. This is the problem of emergence. The philosophy of reductionism, which has been a powerful and successful guiding principle in science, is the idea that we can understand a complex system by breaking it down into its simpler, constituent parts. We can understand the properties of a gas by understanding the behavior of its individual molecules. We can understand the chemistry of a protein by understanding the properties of its atoms. But this approach has its limits. There are many complex systems, from the flocking of birds to the functioning of a city, from the intricate folding of a protein to the emergence of consciousness in a brain, where the behavior of the whole seems to be more than just the sum of its parts. These systems exhibit emergent properties, novel and unpredictable behaviors that arise from the complex, nonlinear interactions of their many components. You cannot understand the beauty and complexity of a flock of starlings by studying a single starling in a cage. You cannot understand the subjective experience of consciousness by studying a single neuron under a microscope. The bridge between the microscopic laws of physics and the macroscopic, emergent realities of our world remains one of the great unsolved frontiers of science. The challenge of understanding complexity is not just a conceptual one, it is also a computational one. The idea that we could, in principle, simulate the entire universe on a powerful enough computer and thus uncover all its secrets is a tempting one. But the theory of computational complexity suggests that this may be an impossible dream. There are many systems in nature that are computationally irreducible. This means that there is no shortcut, no simpler calculation that can predict their future behavior. The only way to know what they will do is to let them do it, to run the simulation, step by step, in real time. The weather is a classic example. Even with the most powerful supercomputers, we cannot predict the weather with perfect accuracy beyond a few days, because the system is so complex and sensitive to initial conditions that small errors in our model are rapidly amplified. The universe itself may be the ultimate, computationally irreducible system. If this is the case, then a complete, predictive knowledge of its future is not just practically, but fundamentally impossible. The universe's story can only be told by living it. This inherent unpredictability is not just a matter of complexity. It is also a matter of the fundamental, probabilistic nature of the quantum world. As we have seen, the universe, at its core, is not deterministic. It is governed by the laws of probability. We can never predict with certainty when a single radioactive atom will decay. We can only know the probability of it decaying in a given time interval. If the universe itself operates on this probabilistic logic, then how can we ever hope to map out a single, definite reality? We are not chasing a single, hidden answer. We are trying to understand a vast and constantly unfolding landscape of possibility. All of these limits the uncertainty of the quantum world, the incompleteness of mathematics, the emergence of complexity, the irreducibility of computation, the probabilistic nature of reality bring us to a final and deeply philosophical question. Are these barriers epistemic, meaning they are a result of our own human limitations of knowledge and perception, or are they ontic, meaning they are a fundamental built-in feature of reality itself? Some philosophers in the instrumentalist tradition would argue that they are epistemic. Science is just a tool for making predictions, and its inability to provide a complete, certain, and final picture of reality is not a failure, but a reflection of its proper limited scope. Others, in the realist tradition, would argue that they are ontic. Our scientific theories, in their very structure, are telling us something deep and true about the nature of reality, that it is, in its essence, incomplete, uncertain, and open-ended. The quest to decode reality, then, is not a quest to find a final, single answer. It is a journey into an ever-deepening mystery. It is a process that requires not just intellectual rigor, but also a profound sense of humility, of wonder, and of acceptance of our own, and perhaps the universe's own, fundamental limitations. The tapestry of reality is not a finished work of art to be admired from a distance. It is a living, breathing, and constantly evolving fabric, and we are not just its observers, but an integral part of its intricate and beautiful weave. The strange and beautiful world of quantum mechanics, with its principles of superposition, entanglement, and measurement, does not just challenge our understanding of the physical world. It also offers a new and profound lens through which to view the deepest mystery of all the nature of our own consciousness. The dialogue between quantum physics and the study of the mind has long been a fertile, if often speculative, ground for inquiry, a place where the most advanced theories of science meet the most ancient questions of philosophy. Could it be that the way we perceive, think, and experience the world is fundamentally tied to the bizarre and counterintuitive logic of the quantum realm? At the very heart of quantum mechanics lies the concept of measurement, the process by which the ghostly probabilistic world of quantum superposition collapses into the definite, singular reality of our classical experience. As we have seen, the role of the observer in this process is deeply enigmatic. While most physicists would argue that a conscious mind is not necessary for the collapse to occur, the very structure of the theory, with its inherent distinction between the unobserved system and the observing apparatus, seems to hint at a special role for information and awareness. This has led some thinkers to propose a more direct link between the quantum and the mental. Could our own subjective experience of a single, coherent reality be a macroscopic reflection of this fundamental process of wave function collapse? Could each moment of conscious awareness be a moment of quantum decision, a point where the vast superpositional potential of our brain's neural activity is resolved into a single, definite thought, feeling, or perception? This brings us to the fascinating idea of cognitive superposition. In our everyday waking lives, our minds often seem to entertain multiple and sometimes contradictory possibilities at once. In a moment of indecision, we can feel the pull of different choices. We can mentally simulate different potential futures. A classical computational model of the brain might see this as a simple, sequential process of weighing different options, but a quantum perspective offers a more radical possibility. Could the brain, at some level, be operating like a quantum computer, capable of holding these different possibilities in a genuine physical state of superposition? Could our subjective experience of indecision be the conscious correlate of an uncollapsed superpositional state in the quantum activity of our neurons? This is a bold and highly speculative idea, but it is one that is being taken seriously by some researchers at the frontiers of neuroscience and quantum biology. The search for a physical quantum basis for consciousness is not just a philosophical fancy. It is a field of active, if controversial, scientific research. We know that biological systems are not just classical chemical machines. There is growing evidence that certain biological processes, from the way that plants perform photosynthesis to the way that birds navigate using the Earth's magnetic field, may be harnessing the strange and powerful effects of the quantum world. Could the human brain be another example of this quantum biology? The orchestrated objective reduction theory, proposed by the physicist Sir Roger Penrose and the anesthesiologist Stuart Hameroff, is the most well-known and specific model for how this might work. It posits that the fundamental units of quantum computation in the brain are not the neurons themselves, but the microtubules, the tiny cylindrical protein structures that form the cytoskeleton of our cells. Penrose and Hameroff argue that the quantum states within these microtubules can exist in a superposition of different configurations, and that these superpositions are the physical basis of our pre-conscious processing. Consciousness in this model arises at the moment of objective reduction, a spontaneous collapse of this quantum superposition that is triggered by a fundamental gravitational instability at the Planck scale. Each of these collapse events, happening many times a second, corresponds to a single, discrete moment of conscious experience. The OR theory is highly speculative and faces a number of significant scientific challenges, particularly the question of how a fragile quantum state could be maintained in the warm, wet, and noisy environment of the brain. But it is a testament to the growing interest in exploring the potential quantum nature of the mind. The observer effect in quantum mechanics, the idea that the act of observation can influence the state of a physical system, also finds a powerful metaphorical, and perhaps even literal, resonance in our understanding of consciousness. Our attention, our awareness, is not a passive spotlight that simply illuminates a pre-existing mental landscape. It is an active, creative force that shapes and transforms our inner world. When we bring a quality of mindful, non-judgmental awareness to a difficult emotion, like fear or anger, we can often feel its energetic quality shift and change. The act of observing it, without being identified with it, seems to collapse its power, to transform it from a solid, overwhelming reality into a more fluid and manageable experience. This is the basis of many contemplative and therapeutic practices. And it is an experience that hints at the possibility that our consciousness is not just a product of the brain, but is a fundamental, causal agent in the brain, a force that can influence the very physical processes that give rise to it. The bridge between the quantum and the classical, the strange and the familiar, may be found in the process of decoherence. As we have seen, decoherence is what explains why we do not experience the world as a constant, blurry superposition. A quantum system, through its unavoidable entanglement with its environment, rapidly loses its quantum coherence. The information about its superposition is spread out into the surrounding world, and for all practical purposes, the system behaves classically. This principle is what safeguards our classical, everyday reality from the bizarre, underlying quantum weirdness. But it also offers a new way to think about the nature of perception itself. Our sensory organs, our eyes, our ears, our skin are macroscopic measuring devices. They are constantly interacting with and entangling with the quantum systems of the external world. The act of perception is a process of decoherence. When a photon from a distant star hits a retinal molecule in your eye, it triggers a cascade of classical chemical events. The quantum information of the photon's superpositional state is effectively measured and collapsed into a definite, classical signal that is then processed by your brain. Our classical perception of the world is, in this sense, a consequence of the constant entropic loss of quantum information. We see a definite, classical world because our very act of seeing is a process that destroys the underlying quantum reality. This leads to a profound and humbling conclusion. The reality we experience is not the full reality. It is a collapsed reality, a simplified and likely very partial representation of a much richer and far stranger quantum world. The discussion of consciousness and quantum mechanics inevitably leads to the age-old debate about free will. A classical, deterministic universe, governed by the clockwork laws of Newton, seems to leave no room for genuine freedom. Our choices would be nothing more than the inevitable outcome of a long chain of prior causes and effects. But the quantum world, with its inherent, irreducible randomness, seems to open a door. The collapse of the wave function is a probabilistic event. The outcome is not predetermined. Some have argued that this quantum indeterminacy could be the physical basis for our experience of free will. Perhaps our choices are not the result of a deterministic, computational process in our brains, but are, at some level, the result of the amplification of these random quantum events. This is a controversial idea, as it seems to equate free will with pure chance, which is not what we usually mean by freedom. But a more sophisticated version of this idea suggests that our conscious mind may be able to influence the probabilities of these quantum events, to steer the collapse of the wave function in a way that is consistent with our intentions, without violating the statistical laws of quantum mechanics. This is a deep and difficult problem, and one that is far from being solved. But the dialogue between quantum mechanics and consciousness, for all its speculative nature, is a powerful and important one. It is a dialogue that is pushing the boundaries of both science and philosophy. It is forcing us to question our most basic assumptions about the nature of reality, of the mind, and of the relationship between the two. It is a reminder that the universe is far more intricate, far more interconnected, and far more wondrous than our classical intuition can ever reveal. And it is an invitation to explore the deep and as yet uncharted territory where the mysteries of the outer cosmos meet the mysteries of our own inner world. The universe is brimming with information. It is encoded in the complex, swirling patterns of a galaxy, in the precise, orbital dance of a planetary system, in the fiery thermonuclear heart of a star, in the elegant double helix structure of a DNA molecule, and in the strange probabilistic wave function of a single subatomic particle. From the grandest cosmic scales to the most infinitesimal quantum ones, information is the thread that weaves the fabric of reality. But what happens to this information over the long and often violent course of cosmic history? Is it preserved forever, a perfect, indelible record of all that has ever been? Or can it be lost, erased, destroyed in the great entropic wash of time? This is one of the most fundamental and deeply debated questions in all of modern physics. A question that touches on the nature of time, of entropy, of black holes, and of the very laws of the universe itself. To understand the fate of information, we must first understand its foundations in both classical and quantum physics. In the classical world, information is, in principle, always preserved. This is a direct consequence of the deterministic nature of classical laws. If you know the precise state of a closed system at one moment in time, the position and velocity of every particle, then the laws of physics allow you to, in principle, calculate its state at any other time, both in the future and in the past. Information is never lost. It is just rearranged. But the quantum world, as we have seen, operates on a different logic. The process of decoherence seems to imply a fundamental loss of information. When a quantum system interacts with its environment, the information about its delicate superpositional state is rapidly spread out and dissipated, becoming, for all practical purposes, irretrievably lost. This is why our macroscopic world appears to be classical, even though it is built from quantum components. The quantum weirdness is constantly being washed away by the entropic tide of environmental interaction. Understanding and controlling this process of decoherence is one of the central challenges in the development of practical quantum technologies. To build a powerful quantum computer, we must find ways to isolate our qubits from their environment, to shield them from the relentless process of decoherence, long enough for them to perform their complex calculations. The quest to build a quantum computer is, in a very real sense, a battle against the informational entropy of the universe. The deep and intimate connection between information and entropy is a cornerstone of modern physics, a connection that is most beautifully illustrated by the laws of thermodynamics. The second law of thermodynamics, as we have seen, states that the entropy, or disorder, of a closed system always increases over time. This is the law that gives time its arrow, but information can be seen as the very opposite of entropy. It is a measure of order, of structure, of reduced uncertainty. When we gain information about a system, we are, in a sense, locally reducing its entropy. This is the paradox of Maxwell's demon, the hypothetical being who could seemingly violate the second law by sorting hot and cold molecules. The resolution to the paradox lies in the realization that the demon itself, in the process of acquiring and processing information, must generate at least as much entropy as it reduces, thus preserving the overall validity of the second law. This connection was made even more explicit by Landauer's principle, which states that the erasure of information is an irreversible, entropy-increasing process. To erase a single bit of information from a computer's memory, you must release a minimum amount of heat into the environment. Information is not an abstract, disembodied entity. It has a real physical cost. It is tied, by the fundamental laws of nature, to the world of energy and entropy. On the grand cosmic scale, the universe itself can be seen as a vast and ancient repository of information. The cosmic microwave background, the faint afterglow of the Big Bang, is not just a uniform glow. Its tiny temperature fluctuations are a snapshot of the primordial information, the quantum seeds from which all the structure in the universe grew, the large-scale distribution of galaxies, the intricate chemical composition of the stars, the complex geological history of a planet. All of these are records, archives of the universe's long and complex evolutionary story. But what is the ultimate fate of all this cosmic information? Does the universe have a finite memory? The accelerating expansion of the cosmos, driven by dark energy, raises a profound and unsettling possibility. If the universe continues to expand at an ever-increasing rate, then the information contained in distant galaxies will eventually be stretched and redshifted into oblivion, lost forever beyond our cosmic event horizon. The observable universe will become an increasingly barren and information-poor place. And the enigmas of dark matter and dark energy add another layer of mystery. Does dark matter, which makes up the vast majority of the matter in the universe, play a role in storing or processing information? Or is it an informationally inert, passive background? And what is the informational nature of dark energy itself? Is it a simple, constant energy of the vacuum, or is it a dynamic, information-rich field that is evolving over time? These are some of the most profound and challenging questions in all of cosmology. Perhaps the most intriguing and challenging intersection between information and the cosmos lies in the nature of gravity itself. For decades, the quest to unify general relativity and quantum mechanics has been the holy grail of theoretical physics, and in recent years, a new and powerful idea has emerged that gravity itself may not be a fundamental force, but an emergent phenomenon, something that arises from the deeper quantum informational structure of the universe. The idea is that the very fabric of space-time is woven from the threads of quantum entanglement, the geometry of space. The curvature that we perceive as gravity is a macroscopic manifestation of the intricate web of quantum correlations between the fundamental constituents of reality. In this view, information is not just in the universe. The universe is information. This is a radical and beautiful vision, and it is one that is supported by the holographic principle. The idea that all the information in a three-dimensional volume can be encoded on its two-dimensional boundary. This principle, which first arose from the study of the thermodynamics of black holes, suggests that our familiar three-dimensional world may be a kind of cosmic hologram, a projection of a more fundamental, two-dimensional informational reality. This would have profound implications for the black hole information paradox. If the information about the matter that falls into a black hole is encoded on its two-dimensional event horizon, then it is never truly lost to the universe. As the black hole evaporates, this information could be subtly and complexly imprinted onto the outgoing Hawking radiation, thus preserving the fundamental principles of quantum mechanics. And what of the ultimate fate of the universe in this informational picture? If the universe is destined for a heat death, a state of maximum entropy where all energy is evenly distributed and no useful work can be done, would this also be a state of information death? Would all the complex ordered information that has been created over billions of years of cosmic and biological evolution be lost in a final, uniform sea of thermal noise, or could information persist? Even in this seemingly final state, some speculative theories suggest that even in a heat-death scenario, the quantum fluctuations of the vacuum would continue, and that over immense, almost unimaginable timescales, new, ordered structures could spontaneously fluctuate into existence. The universe could, in a sense, be reborn from its own informational ashes. The study of information in physics is a rapidly evolving and incredibly exciting field. It is a field that is blurring the lines between physics, computer science, and philosophy. It is forcing us to rethink our most basic concepts of reality, of space, of time, of causality. And it is a field that is driven by a single, powerful, and unifying idea that to understand the universe, we must understand its information. The cosmos is not just a collection of matter and energy. It is a story, a message, a vast and ongoing computation. And in learning to read this cosmic code, we are not just deciphering the secrets of the universe. We are also, in a very real sense, discovering the deep informational nature of ourselves. The future of humanity has always been inextricably linked to our ability to create, to process, and to transmit information. From the invention of language and writing to the development of the printing press and the Internet, every major leap in our information technology has been a major leap in our civilization. And today, we stand on the cusp of a new and potentially even more transformative revolution. A revolution that is being driven by the strange and powerful logic of the quantum world. The future of information is a story of two converging technologies, artificial intelligence and the quantum internet. And their combination holds the promise to redefine not just our technology, but the very fabric of human existence. Artificial intelligence, once the stuff of science fiction, is now a ubiquitous part of our everyday lives. It is in the virtual assistants that organize our schedules, in the recommendation algorithms that shape our cultural tastes, in the sophisticated systems that help doctors to diagnose disease and scientists to analyze vast and complex data sets. The power of modern AI lies in its ability to learn from data, to recognize patterns, and to make predictions with a speed and an accuracy that can far surpass human capabilities. But for all its power, our current AI is still limited. It is a form of narrow AI, a system that is incredibly good at performing specific, well-defined tasks, but that lacks the general, flexible, and creative intelligence of a human mind. The story of AI is still in its early chapters, and the next, and perhaps most exciting, chapter may be written in the language of quantum information. The concept of quantum information, as we have seen, is a radical departure from the classical binary logic of our current computers. A quantum computer, by harnessing the principles of superposition and entanglement, can process information in a fundamentally new and more powerful way. It can explore a vast, multidimensional computational space simultaneously, giving it the potential to solve certain classes of problems that are, for all practical purposes, unsolvable for any classical machine. Imagine an AI system that is not limited by the linear, step-by-step logic of a classical computer, but can think in the rich, probabilistic, and superpositional language of the quantum world. This is the promise of quantum AI. Why? A quantum AI could, in principle, analyze a vast and complex landscape of possibilities in an instant, allowing it to solve complex optimization problems, to design new materials with novel properties, or to discover new drugs by simulating the quantum behavior of molecules with perfect fidelity. It could be an engine of scientific discovery and technological innovation of unprecedented power. But the quantum revolution is not just about computation, it is also about communication. And this is where the second part of our story begins, the development of the quantum internet. A classical internet transmits information as bits of data encoded in pulses of light or electrical signals. A quantum internet would transmit information as qubits encoded in the quantum states of single particles, like photons, and its primary, and most revolutionary, feature would be its inherent and perfect security. As we have seen, the principles of quantum mechanics, like the no-cloning theorem and the observer effect, make it impossible to intercept or copy a quantum communication without being detected. A quantum internet would be a truly unhackable network, a development that could revolutionize every industry that relies on the secure transmission of data, from finance and government to healthcare and defense. But the potential of a quantum internet extends far beyond secure communication. It would also be a network that can transmit entanglement. It would allow us to create and distribute these strange, non-local quantum connections between distant quantum computers, linking them together into a single, global quantum computational network. This would allow us to tackle problems that are too large and complex for even a single, powerful quantum computer. It would be a new kind of global collaboration, a new way of harnessing the collective, computational power of the quantum world. Now, let us think even bigger, even more speculatively. What is the ultimate, long-term potential of this quantum information revolution? The astrophysicist Nikolai Kardashev famously proposed a scale for categorizing hypothetical and advanced extraterrestrial civilizations based on their ability to harness energy. A Type 1 civilization is one that can harness all the energy of its home planet. A Type 2 can harness all the energy of its host star, and a Type 3 can command the power of its entire galaxy. We can imagine a similar scale for the mastery of information. What if a future advanced civilization could learn to harness and process information on a cosmic scale? What if they could build a galactic-scale quantum internet, a network that connects not just computers, but planets, stars, and perhaps even different regions of space-time? This is a provocative and highly speculative notion, but it is a logical, long-term extension of the technological trajectory we are on. If information is the currency of intelligence, then the ability to manage information on a cosmic scale could allow a civilization to unlock secrets of the universe that we can't even begin to comprehend. Could this be an evolutionary milestone for advanced life? Could the mastery of quantum information be the key to reaching a new and higher level of cosmic consciousness? Naturally, these bold and futuristic ideas spark a host of profound ethical and philosophical questions. The development of a true general artificial intelligence, whether classical or quantum, would be a watershed moment in the history of life on Earth. How would we ensure that such an intelligence is aligned with human values? How would we prevent it from being misused? What would be our own role and purpose in a world where we are no longer the most intelligent beings on the planet? These are not just technical challenges, they are deep, societal, and existential ones. Similarly, the development of a global quantum internet, while offering the promise of perfect security, also raises questions about privacy, surveillance, and control. Who would own and control this new fundamental layer of our information infrastructure? How would we ensure that its benefits are distributed equitably and that it does not become a tool for creating an even wider gap between the haves and the have-nots of the information age? The democratization of these powerful new technologies will be one of the most critical challenges of the coming century. And of course, there are the skeptics. Some argue that the warm, wet, and noisy environment of a biological brain is simply not conducive to the kind of delicate, coherent quantum processes that would be needed for a quantum mind. Others argue that even a powerful quantum AI would never be able to replicate the true, subjective experience of human consciousness, with all its intuition, its creativity, its capacity for love and sorrow. These are valid and important critiques, and the debate is far from settled. But even if the most ambitious claims for quantum consciousness and AGI do not come to pass, the journey itself is transforming our world. The promise of quantum information is reshaping our understanding of artificial intelligence. The development of the quantum internet is redefining the future of communication. And the futuristic vision of a civilization that can harness information on a cosmic scale is providing a new and powerful lens through which to view our own long-term evolutionary future. The future of information is not just about faster computers or more secure networks. It is about redefining what it means to live in an interconnected, intelligent, and information-rich world. It is about uncovering new truths, not just about the universe, but about ourselves. It is about understanding what a civilization can achieve when its technological innovation is guided by its deepest imaginative and ethical aspirations. As we conclude this exploration, the question we are left with is not, what is the future of information? But rather, How will we choose to shape our future with the new and powerful forms of information that we are now, for the first time in history, beginning to create? The possibilities are infinite, the questions are profound, and the answers, for now, are waiting for us in the strange, beautiful, and endlessly creative quantum unknown. Imagine an object so dense, so heavy, that its own gravity becomes an inescapable trap. Picture a point in space where the familiar rules of our universe are bent and broken, where time itself can grind to a halt, and where not even light, the fastest thing in the cosmos, can escape. This is the world of the black hole, one of the most extreme and enigmatic phenomena in all of nature. According to Albert Einstein's general theory of relativity, when a sufficient amount of matter is compressed into a sufficiently small volume, the force of gravity becomes so overwhelming that it creates a one-way membrane in space-time, a point of no return known as the event horizon. Anything that crosses this boundary is lost to the outside universe forever, pulled inexorably towards a central singularity, a point of infinite density where our current laws of physics break down. The size of this event horizon, the Schwarzschild radius, depends on the mass of the object. For our own sun to become a black hole, it would need to be squeezed down to a diameter of just 3 kilometers. At that point, its density would be astronomical, far beyond anything we encounter in our everyday world. For smaller objects, the powerful quantum forces that operate between subatomic particles, the electromagnetic force and the nuclear forces, are strong enough to resist the inward pull of gravity, preventing them from collapsing into such an extreme state. But for the most massive stars in the universe, a different fate awaits. Black holes are not just a theoretical curiosity. They are a ubiquitous feature of our cosmos, and they come in a vast range of sizes. Stellar mass black holes are the ghosts of dead stars. When a star, more than about 10 times the mass of our sun, exhausts its nuclear fuel, it can no longer support its own weight against the crushing force of gravity. Its core collapses catastrophically, triggering a spectacular supernova explosion that blasts its outer layers into space. What remains behind is a compact remnant, a black hole with a mass a few times that of our sun. Our own Milky Way galaxy is thought to be littered with over 1 billion of these stellar ghosts, most of them dark and invisible, wandering silently through the interstellar void. We can only detect them indirectly when they are locked in a binary system with a normal star, their immense gravity pulling material from their companion into a glowing, superheated accretion disk. At the other end of the scale are the supermassive black holes, the true giants of the cosmos. These behemoths, with masses ranging from millions to billions of times that of our sun, are thought to reside at the heart of nearly every large galaxy, including our own. At the center of the Milky Way lurks Sagittarius A, a supermassive black hole with a mass of about 4 million suns. These galactic monsters are the engines that power the most luminous objects in the universe, quasars. A quasar is an incredibly bright, distant galactic nucleus, where a supermassive black hole is actively feeding on a vast disk of gas and dust, releasing an amount of energy that can outshine its entire host galaxy by a factor of thousands. Between these two extremes lies a more elusive class, intermediate mass black holes. These are thought to form from the collapse of the very first generation of stars, population 3 stars, which were much more massive than the stars we see today, with masses over 100 times that of our sun. These primordial giants would have burned through their fuel very quickly, collapsing directly into intermediate mass black holes and potentially triggering some of the powerful gamma-ray bursts we observe in the distant universe. All of these black holes, from the stellar to the supermassive, are considered macroscopic. They are large enough that their behavior is, for the most part, well described by the classical laws of Einstein's general relativity. But there may be another, much stranger, class of black holes. A class for which the bizarre rules of the quantum world become all important. These are the primordial black holes, hypothetical objects that may have formed not from the collapse of stars, but from the extreme, high-density conditions of the very early universe, just a fraction of a second after the Big Bang. These primordial black holes could have a vast range of masses, from the supermassive down to the microscopic. A primordial black hole with a mass less than that of our moon could be smaller than a micron. Yet its gravitational influence could still be significant, and some have speculated that these objects could even constitute the mysterious dark matter that makes up the bulk of the universe's mass. It is at this microscopic scale that our classical understanding of black holes begins to break down, and a new, more profound, and more mysterious picture begins to emerge. In 1974, the physicist Stephen Hawking made a discovery that would forever change our understanding of black holes and would forge a deep and unexpected link between the two great pillars of modern physics, general relativity and quantum mechanics. He showed that black holes are not, in fact, completely black. Due to quantum effects at the very edge of the event horizon, they should slowly emit a faint thermal radiation, now known as Hawking radiation. This discovery was a theoretical tour de force, a beautiful and subtle calculation that showed how the constant roiling sea of virtual particles in the quantum vacuum could be influenced by the intense gravity of a black hole. In the empty space near an event horizon, a virtual particle-antiparticle pair can be created. Normally, this pair would quickly annihilate each other and disappear. But if one particle falls into the black hole while the other escapes, the escaping particle can become a real particle, carrying away a tiny amount of the black hole's mass energy. The black hole, in effect, radiates. The temperature of this radiation is inversely proportional to the black hole's mass. The smaller the black hole, the hotter it is, and the more rapidly it radiates. For a large, stellar mass black hole, this temperature is incredibly low, far colder than the cosmic microwave background, making the radiation practically undetectable. But for a small, primordial black hole, the temperature could be incredibly high. A black hole with the mass of a large mountain would have a temperature of about 10 to the power of 12 Kelvin, and it would radiate away its mass not just as photons, but as a shower of electrons, positrons, and other energetic particles. This process of radiation means that black holes are not eternal. They evaporate. As a black hole radiates, it loses mass, which, due to the inverse relationship, causes it to get hotter and radiate even faster. This creates a runaway process, an accelerating evaporation that culminates in a final, explosive burst of energy. The lifetime of a black hole depends dramatically on its initial mass. A solar mass black hole would take an almost unimaginable 10 to the power of 64 years to evaporate, far longer than the current age of the universe. But a primordial black hole with a mass of about 10 to the power of 12 kilograms would have a lifetime of roughly 10 billion years, about the age of our universe. This means that such black holes, if they were formed in the Big Bang, should be exploding right now, releasing their final energetic death cry in a flash of gamma rays. The search for these telltale flashes is an active, if so far unsuccessful, area of observational astronomy. The black holes that are small enough to be significantly affected by these quantum processes, those with masses below about 10 to the power of 12 kilograms, are what we call quantum black holes. Their behavior is no longer governed solely by classical gravity, but by a complex interplay between general relativity, quantum field theory, and thermodynamics. Hawking's discovery was a monumental first step towards a unified theory of quantum gravity, a theory that could describe the universe at its most extreme and fundamental level. But it was only a first step. His analysis was semi-classical, meaning it treated the radiating particles quantum mechanically, but treated the space-time of the black hole classically. A full understanding of the formation and evaporation of the smallest possible black holes. Those with a mass and size approaching the Planck scale, the fundamental limit where the effects of quantum gravity become dominant, will require a true, and as yet undiscovered, theory of everything. Such a theory might reveal even stranger possibilities, such as the idea that an evaporating black hole does not disappear completely, but leaves behind a tiny, stable, Planck mass relic, a quantum fossil that could hold the secrets of the information that fell into the black hole. The quest for a theory of quantum gravity, the holy grail of modern theoretical physics, has led scientists down a number of strange and beautiful paths. And one of the most intriguing of these is the idea of extra hidden dimensions of space. This is a concept that dates back to the 1920s, when the physicists Theodore Kaluza and Oscar Klein proposed that our universe might have a fifth dimension, a dimension that is curled up, or compactified, into a tiny circle at every point in our familiar three-dimensional space. They showed that if this were the case, then Einstein's theory of gravity in 5 dimensions would look, in our 4-dimensional world, like a combination of gravity and electromagnetism. It was a beautiful and elegant idea, a first, tantalizing hint that the different forces of nature could be unified through the geometry of higher dimensions. The idea of extra dimensions was later revived and expanded in the context of string theory. In its modern form, known as M-theory, the theory requires the existence of a total of 11 space-time dimensions, 10 of space and 1 of time. The extra 7 spatial dimensions are thought to be curled up into a complex, 6-dimensional geometrical shape known as a Calabi-Yau manifold. The precise shape and size of this manifold determines the vibrational patterns of the fundamental strings, and therefore, the properties of all the particles and forces in our universe. In the standard picture, these extra dimensions are thought to be incredibly small, on the order of the Planck length. This would mean that they have no noticeable effect on the behavior of macroscopic black holes. But in some, more recent, brain world models, it is possible that some of these extra dimensions are much larger. In these models, the particles and forces of the standard model are confined to our 3-dimensional brain, while gravity is free to propagate in the higher dimensional bulk. This could have a dramatic effect on the strength of gravity at short distances. The familiar inverse square law of gravity would break down, and gravity would become much, much stronger at scales comparable to the size of the extra dimensions. This has a profound implication, the true of fundamental scale of quantum gravity. The Planck scale could be much lower than the traditional value of 10 to the power of 19 electron volts. It could, in fact, be as low as a few tera-electron volts, a range of energy that is just now being probed by our most powerful particle accelerator, the Large Hadron Collider. This raises the astonishing and exciting possibility that we could create microscopic quantum black holes in the laboratory. The LHC works by accelerating protons to nearly the speed of light and then smashing them together. Each proton carries an energy of around 7 tera-electron volts. In a head-on collision, the total energy is 14 tera-electron volts, all concentrated in a tiny subatomic volume. In the standard picture of gravity, this is far, far too low an energy to create a black hole. The proton's mass is about 10 to the power of 19 times smaller than the Planck mass, and the density achieved in a collision is many orders of magnitude below the Planck density required for gravitational collapse. To create a black hole in a collision, we would need to accelerate a proton to the Planck energy, an energy that is a quadrillion times higher than what the LHC can achieve. Building such an accelerator would require a machine the size of our galaxy. But if the idea of large extra dimensions is correct, and the true Planck scale is in the tera-electron-volt range, then the story changes completely. The high-energy collisions at the LHC could, in principle, have enough energy to briefly compress a sufficient amount of mass energy into a small enough volume to create a tiny microscopic black hole. These would not be the dangerous galaxy-eating monsters of science fiction. They would be subatomic in size, and they would evaporate almost instantaneously in about 10 to the power of minus 27 seconds via Hawking radiation. They would decay into a spectacular spherical burst of high-energy particles, photons, electrons, quarks, gluons that would light up our detectors like a microscopic firework. A unique and unmistakable signature of new exotic physics. The search for such events has been one of the major goals of the LHC experimental program. So far, no evidence for the production of microscopic black holes has been found. This has placed strong constraints on many of the models with large extra dimensions, pushing the possible scale of quantum gravity to higher and higher energies. But the search continues. The discovery of microscopic black holes at the LHC would be a scientific revolution of the highest order. It would be the first direct experimental evidence for the existence of extra dimensions of space. It would provide us with a laboratory to study the physics of quantum gravity, to test the predictions of Hawking radiation, and to probe the very fabric of space-time at its most fundamental level. It would be a window into a new, hidden reality. A reality that has, until now, been completely inaccessible to us. The discovery of Hawking radiation and the subsequent paradox of information loss has been one of the most powerful drivers of theoretical progress in physics for the past 50 years. It is a problem that lies right at the intersection of our two most fundamental theories, general relativity and quantum mechanics, and its resolution is thought to be a crucial key to unlocking the secrets of quantum gravity. At its heart, the paradox is a clash of two, seemingly inviolable principles. General relativity, with its description of a smooth space-time and an absolute event horizon, seems to imply that any information that falls into a black hole is lost to the outside universe forever, causally disconnected and irretrievable. Quantum mechanics, on the other hand, insists on the principle of unitarity, the idea that information is never truly destroyed. The total amount of information in a closed system must be conserved. A process may be scrambled, its information hidden in complex correlations, but it can, in principle, always be unscrambled. So, what happens when a black hole, which has swallowed a vast amount of information, completely evaporates into a seemingly random thermal bath of Hawking radiation? Is the information lost, in violation of quantum mechanics, or does it somehow get out, in violation of general relativity's principle of locality and causality? This is the information paradox for many years. Stephen Hawking himself was a firm believer in information loss. He argued that the process of black hole evaporation was fundamentally non-unitary, and that we would have to modify the laws of quantum mechanics to accommodate it. But most of the theoretical physics community, particularly those working in string theory, resisted this conclusion. The principle of unitarity is so central to the structure of quantum mechanics that to abandon it would be to abandon the very foundations of our most successful physical theory. This led to a decades-long search for a mechanism by which the information could escape. One of the most powerful and influential ideas to emerge from this search is the holographic principle, first proposed by Gerard 't Hooft and later developed by Leonard Susskind. The principle was motivated by the discovery that the entropy of a black hole, its information content, is proportional not to its volume, as one might expect, but to the area of its event horizon. This is a strange and profound result. It suggests that all the information about the three-dimensional interior of a black hole can be somehow encoded on its two-dimensional surface. This is like a hologram, where a two-dimensional film can encode all the information needed to create a three-dimensional image. The holographic principle generalizes this idea to the entire universe. It suggests that the reality we perceive as a three-dimensional space with gravity might be a holographic projection of a more fundamental two-dimensional quantum field theory that lives on the boundary of our space-time, a theory that does not include gravity. This is the essence of the ADS-CFT correspondence, a specific and powerful mathematical realization of the holographic principle discovered by Juan Maldacena, which shows an exact equivalence between a theory of gravity in a five-dimensional anti-de Sitter space and a four-dimensional quantum field theory living on its boundary. This correspondence provides a powerful tool for studying quantum gravity, as it allows us to translate difficult problems in gravity into more tractable problems in a non-gravitational quantum field theory, a theory that is, by definition, unitary. In the context of the information paradox, the holographic principle suggests that the information is never truly inside the black hole in the classical sense. It is stored on the event horizon, and as the black hole evaporates, this information is slowly and subtly encoded in the quantum correlations of the outgoing Hawking radiation. The process is unitary, and no information is lost. Another, more recent, and even more startling idea is the ER-EPR conjecture, proposed by Leonard Susskind and Juan Maldacena. This conjecture proposes a deep and unexpected connection between two of Einstein's most famous ideas, the spooky action at a distance of quantum entanglement and the concept of a wormhole or Einstein-Rosen bridge. The conjecture states that two entangled particles are, in a sense, connected by a microscopic, non-traversable wormhole. The strange, non-local correlation of entanglement is a manifestation of this deep, geometrical connection in space-time. In the context of a black hole, this idea has profound implications. The outgoing Hawking radiation is entangled with the particles that fell into the black hole. The ERR-EPR conjecture would suggest that the inside of the black hole is geometrically connected to the outgoing radiation via a vast network of microscopic wormholes. The information is not trapped inside. It is non-locally connected to the outside. These are highly abstract and mathematical ideas, and they are still the subject of intense research and debate. But they are a testament to the incredible creativity and power of theoretical physics. They show how a deep conceptual paradox, born from the clash of our two greatest theories, can become a powerful engine for discovery, leading us to new and profound insights into the nature of space-time, of information, and of reality itself. The black hole information paradox is not just a technical puzzle. It is a koan, a riddle that is forcing us to abandon our classical intuitions and to embrace a new, more holistic and more deeply quantum vision of the cosmos. The formation of black holes is a story of gravitational triumph, a cosmic drama where the relentless inward pull of gravity overcomes all other forces of nature. The most common pathway to a black hole is through the death of a massive star. A star, for most of its life, is a battlefield, a delicate balance between two opposing forces. Gravity, the force that pulls all of its matter inwards, is constantly trying to crush the star. This is counteracted by the outward pressure generated by the intense heat and radiation from the nuclear fusion reactions in its core. As long as the star has fuel to burn, this hydrostatic equilibrium is maintained. But when a massive star, one with a mass more than about 25 times that of our Sun, exhausts its nuclear fuel, the story changes. The fusion reactions in its core cease, the outward pressure vanishes, and gravity wins. The core of the star collapses catastrophically under its own immense weight. This collapse is an incredibly rapid and violent event. In a fraction of a second, a region of matter the size of the Earth is crushed down to a size smaller than a city, reaching densities that are almost beyond comprehension. The outer layers of the star, no longer supported by the core, come crashing down, bounce off the super-dense, newly formed protoneutron star, and are blasted out into space in a spectacular supernova explosion, one of the most energetic events in the universe. But for the most massive stars, even the immense pressure of the neutrons, the neutron degeneracy pressure that supports a neutron star, is not enough to halt the collapse. The gravitational pull is so overwhelming that the core continues to collapse indefinitely, down to a point of infinite density, a singularity. An event horizon forms around this singularity, and a new stellar mass black hole is born. This is the standard picture, but recent observations and theoretical work have revealed a more complex and nuanced story. For stars in a certain mass range, roughly between 8 and 25 solar masses, the collapse of the core can be temporarily halted, forming a neutron star. But the fallback of material from the supernova explosion can then push the mass of the neutron star over its critical limit, causing it to subsequently collapse into a black hole. For even larger stars, those with masses above about 40 times that of the Sun, the collapse can be so rapid and so powerful that it does not even produce a traditional supernova. The star collapses directly into a black hole, swallowing its own explosion in a phenomenon known as a collapser. These events are thought to be the engines behind some of the most powerful explosions in the universe. The long-duration gamma-ray bursts. The formation of supermassive black holes, the behemoths that reside at the centers of galaxies, is a more complex and still not fully understood story. They are too massive to have formed from the collapse of a single star. Instead, they are thought to have grown over cosmic time through a combination of processes. They may have started as seed black holes in the early universe, either from the collapse of the very first massive population 3 stars, or from the direct collapse of vast clouds of primordial gas. These seed black holes would have then grown over billions of years by accreting gas and dust from their host galaxies, and by merging with other black holes during galactic collisions. The James Webb Space Telescope is providing crucial new insights into this process by observing some of the most distant quasars, which are powered by supermassive black holes that had already grown to billions of solar masses when the universe was less than 1 billion years old. The existence of these massive black holes so early in cosmic history is a major challenge to our models of their formation and growth, suggesting that the process may have been much more rapid and efficient than we previously thought. The formation of a black hole is not just an astrophysical event, it is a transformation of the very fabric of reality. A place where matter is crushed out of existence and the laws of physics are pushed to their absolute limits. It is a one-way journey into a realm of mystery, a place from which no information can return. Or so we thought. The no-hair theorem is a profound and elegant statement about the nature of black holes in the context of classical general relativity. It is a concept that strips black holes of all their complexity and reduces them to objects of almost perfect simplicity. The theorem, which was developed through the work of physicists like Werner Israel, Brandon Carter, and Stephen Hawking, states that a stable, stationary black hole, regardless of the intricate details of the matter that collapsed to form it, can be completely and uniquely described by just 3, and only 3, externally observable properties: its total mass, its total electric charge, and its total angular momentum, or spin. All other information about the matter that fell in its chemical composition, its temperature, its shape, its texture is seemingly lost forever behind the event horizon. The black hole, in this sense, has no hair. It has no other distinguishing features, No complex individual characteristics. All black holes with the same mass, charge, and spin are identical and indistinguishable from the outside. This is a remarkable statement. It means that if you were to make a black hole by collapsing a vast cloud of hydrogen gas, and another black hole of the same mass by collapsing a collection of old television sets, the final, stable black holes would be absolutely identical. The immense complexity and information content of the initial matter is wiped clean, leaving behind only the three conserved quantities of mass, charge, and angular momentum. The no-hair theorem is a powerful illustration of the information loss problem. It is the classical statement that a black hole is a perfect information sink. The geometry of space-time around a black hole is determined solely by these three parameters. A non-rotating, uncharged black hole is described by the simple Schwarzschild metric. A rotating black hole is described by the Kerr metric, and a charged, non-rotating black hole is described by the Reissner-Nordstrom metric. The most general case, a rotating, charged black hole, is described by the Kerr-Newman metric. These four solutions to Einstein's field equations are thought to describe all possible, stable, black holes in our universe. This simplicity, however, is a feature of the classical world. When we begin to consider the quantum nature of black holes, the picture becomes more complex. Quantum mechanics suggests that black holes should have a vast number of internal microscopic states, a microscopic hair that is not visible from the outside. The entropy of a black hole, which is proportional to the area of its event horizon, is a measure of this hidden internal information. The challenge for a theory of quantum gravity is to provide a microscopic, statistical explanation for this entropy, to count the number of quantum states that correspond to a given macroscopic black holes. String theory, for example, has had some remarkable successes in this area. Being able to precisely calculate the entropy of certain highly symmetric, extremal black holes by counting the number of ways that fundamental strings and branes can be configured to produce the same mass, charge, and spin. This is seen as one of the major triumphs of the theory, a sign that it is on the right track towards a quantum description of gravity. The no-hair theorem, then, may be a classical approximation. From a distance, a black hole may appear simple and featureless, but up close, at the quantum level, it may be a rich and complex object. Its event horizon a shimmering, holographic surface that encodes a vast amount of hidden information. The question of whether this information is ultimately lost or preserved is the question that lies at the heart of the information paradox, and it is a question that will likely not be fully answered until we have a complete and consistent theory of quantum gravity. The theoretical possibility of creating microscopic black holes in high-energy particle collisions, while still unconfirmed, has opened up a fascinating new frontier in experimental physics. It is an idea that connects the largest objects in the universe with the smallest, the force of gravity with the world of particle physics, and it offers a potential, albeit challenging, path to probing the exotic realm of quantum gravity in the laboratory. The production of a black hole in a collision is governed by a simple principle known as the Hoop conjecture, proposed by the physicist Kip Thorne. It states that a black hole will form if, and only if, a sufficient amount of mass energy is compressed into a region of space that is smaller than its own Schwarzschild radius. In the context of a particle collision, this means that the two colliding particles must get closer to each other than the Schwarzschild radius corresponding to their total center of mass energy. In the standard four-dimensional picture of gravity, this is an impossible feat for any conceivable particle accelerator. The Planck energy. The energy at which gravitational effects become strong is about 10 to the power of 16 times higher than the energy of the LHC. But in models with large extra dimensions, as we have seen, the true scale of quantum gravity could be much lower, potentially within the reach of the LHC. If this is the case, then in a tiny fraction of the proton-proton collisions at the LHC. The two colliding partons could get close enough to form a microscopic black hole. The probability, or cross-section, for this process can be estimated using simple, geometrical arguments. It is roughly equal to the geometric area of the black hole's event horizon, which is proportional to the square of its Schwarzschild radius. The details of the process are complex, involving the gravitational shock waves of the two ultra-relativistic particles, a phenomenon described by the Eichelberg-Sechsel metric. But the basic idea is that a closed, trapped surface, the mathematical definition of an event horizon, can form in the collision, signaling the birth of a black hole. These microscopic black holes would be incredibly unstable, evaporating almost instantaneously through Hawking radiation. The specific way they decay, however, would be a powerful probe of new physics. In the standard model, a black hole should radiate democratically, emitting all types of particles with a probability that depends only on their mass and spin. But in models with extra dimensions, the black hole could preferentially radiate particles into the higher dimensional bulk, such as gravitons. This would result in a missing energy signature in our detectors, a telltale sign of the existence of extra dimensions. The Hawking radiation from these black holes would also be thermal, with a temperature that depends on the black hole's mass. By measuring the spectrum of the decay products, we could, in principle, measure the temperature of the black hole and test the predictions of Hawking's theory. Furthermore, the final stages of the black hole's evaporation, when it reaches the Planck scale, are a realm where a full theory of quantum gravity is needed. The specific particles and energies emitted in this final burst could provide crucial clues about the nature of this ultimate theory. Are they stable? Planck mass remnants is information preserved. The decay of a microscopic black hole would be a window into the most fundamental secrets of nature. The search for these exotic events at the LHC has, so far, come up empty. No signs of black hole production have been observed. This has placed stringent limits on the models with large extra dimensions, pushing the possible scale of quantum gravity to ever higher energies. It seems that if extra dimensions exist, they are smaller, or their geometry is more complex than the simplest models predicted. But the quest is not over. The LHC is continuing to collect data at higher energies and higher luminosities. And future. More powerful accelerators are being planned. The dream of creating a black hole in the laboratory, of holding a piece of quantum space-time in our hands, is a dream that still inspires and motivates a generation of physicists. It is a long shot, to be sure, but it is a shot worth taking. For the scientific prize would be nothing less than a revolution in our understanding of the universe. In the absence of direct experimental evidence for quantum gravity from particle accelerators, physicists have turned to another, more subtle and more theoretical approach: effective field theory. This is a powerful and pragmatic framework that allows us to study the low-energy consequences of a high-energy theory without knowing all the details of that theory. The basic idea is to integrate out the high-energy physics, to average over the effects of the heavy, unknown particles and the quantum gravitational fluctuations, and to see what subtle, residual effects they leave behind on the low-energy physics that we can observe. In the context of quantum gravity, this means that we can write down and use effective action for our low-energy world, which consists of Einstein's general relativity and the standard model of particle physics, plus an infinite series of small, higher-dimensional correction terms. These correction terms are suppressed by powers of the Planck scale, the fundamental scale of quantum gravity. They represent the faint, low-energy echoes of the unknown, high-energy physics. While these effects are incredibly small, they are, in principle, measurable. And by precisely measuring the properties of particles and forces at low energies, we can place constraints on the possible values of the coefficients of these correction terms, giving us an indirect, but powerful, glimpse into the nature of quantum gravity. One of the most important of these correction terms is a potential non-minimal coupling between the Higgs boson and the curvature of space-time. The Higgs boson is a unique and special particle. It is the only fundamental scalar particle in the Standard Model, and its associated field, the Higgs field, is what gives mass to all the other fundamental particles. It is natural to expect that the Higgs field would have a direct coupling to the geometry of space-time, a coupling that is represented by a term in the effective action. This coupling has profound cosmological implications. In the early universe, during the period of cosmic inflation, the Higgs field itself could have played the role of the inflaton, the field that drove the exponential expansion. This is the idea behind Higgs inflation models. The viability of these models depends crucially on the value of this non-minimal coupling constant. By precisely measuring the properties of the cosmic microwave background, which carries the imprint of the inflationary epoch, we can place constraints on these models and, indirectly, on the nature of the interaction between the Higgs field and gravity. Another, related area of research is the effect of these quantum gravitational corrections on the unification of the fundamental forces. In grand unified theories, the strong, weak, and electromagnetic forces are all thought to emerge from a single unified force at very high energies. The success of these theories depends on the precise way that the strengths of the three forces evolve with energy and meet at a single point. The quantum gravitational correction terms can affect this running of the coupling constants, potentially altering the predictions of GUTs and offering a new way to probe the physics at the unification scale. Effective field theory is a subtle and powerful tool. It allows us to make progress in the absence of a complete theory. It is a way of listening for the faint, low-frequency whispers of the high-energy, quantum gravitational world. And while it may not give us the full symphony, it can provide us with crucial notes, with hints and clues that can guide us in our long and difficult quest to construct a final, unified theory of everything. It is a beautiful example of how precision measurements in the world we can access can shed light on the deep and mysterious realities of the world we cannot. The world of quantum gravity is not just a world of microscopic black holes and extra dimensions. It is a world where the very concepts of causality and locality, the bedrock of our classical intuition, may break down. In a classical relativistic world, information cannot travel faster than light, and events can only be influenced by other events in their past light cone. But in a theory of quantum gravity, where space-time itself is subject to quantum fluctuations, this rigid causal structure may become fuzzy or even non-existent at the Planck scale. This has led to the exploration of non-local and acausal theories. Theories where distant points in space-time can be connected in ways that defy our normal understanding. One of the most interesting and well-developed of these is the Leawick model, a type of quantum field theory that introduces new heavy particles with a peculiar property. They have a wrong sign propagator, which effectively means they can travel backwards in time for very short distances. This seemingly bizarre feature has a remarkable consequence. It can cancel out some of the problematic infinite quantities that plague standard quantum field theories, making the theory finite and more mathematically consistent. The price to pay for this mathematical elegance is a tiny, microscopic violation of causality. These violations are confined to the Planck scale and are too small to be observed in any macroscopic experiment. So they do not lead to the familiar paradoxes of time travel, but they do suggest that at the most fundamental level, the strict linear arrow of time may not hold. The universe may have a built-in, microscopic causality that is an essential part of its structure. The study of gravitational scattering at very high energies, near the Planck scale, has also provided hints of non-local and acausal effects. When we try to calculate the probability of two gravitons scattering off each other at these extreme energies using our standard techniques, we run into problems with unitarity, the principle that probabilities must always add up to 1. However, by using a technique called resumation, where we take into account an infinite series of quantum loop corrections, it is possible to restore unitarity. But this comes at a cost. The resumed graviton propagator, the mathematical object that describes the propagation of a graviton, develops new, complex poles. These poles do not correspond to normal, stable particles. They represent short-lived, unstable resonances, which have been interpreted as the quantum precursors of microscopic black holes. These quantum black holes are not the classical objects of general relativity. They are fuzzy, quantum states that have some of the properties of a black hole, but are not described by a classical singularity or event horizon. And one of their most striking features is that they seem to introduce a degree of non-locality and a causality into the theory. This is perhaps not surprising. A black hole, even a classical one, is a fundamentally non-local object. Its event horizon is a global property of the spacetime. The fact that the quantum precursors of black holes seem to be tied to a microscopic violation of causality is a deep and tantalizing clue. It suggests that the resolution of the conflict between gravity and quantum mechanics may require us to abandon one of our most deeply held intuitions, the idea of a strict, linear, and unbreakable chain of cause and effect. This has led to the development of two related concepts, self-healing and classicalization. Self-healing is the idea that the theory of quantum gravity has a built-in mechanism to prevent the formation of true, problematic singularities. As we approach the Planck scale, the quantum black hole resonances become the dominant effect, effectively healing the spacetime and preventing it from becoming infinitely curved. Classicalization is the idea that as we go to higher and higher energies, the quantum black hole states become more and more numerous and begin to behave more and more like a classical macroscopic black hole. The system, in a sense, classicalizes itself. In this picture, there is a minimal length in nature, on the order of the Planck length, below which it is impossible to probe. Any attempt to do so by using higher and higher energy probes will simply result in the creation of a larger and larger black hole, which actually hides, rather than reveals, the short-distance structure of spacetime. This is a profound and beautiful picture. It suggests that the universe has a built-in, self-regulating mechanism that protects itself from the paradoxes and infinities that have plagued our theories. It suggests that the final theory may be one that is not just mathematically consistent, but is also, in a deep sense, self-healing. The rich and varied zoo of black holes predicted by our theories, the spinning, the charged, the higher dimensional, provides a vast theoretical laboratory for exploring the intricate interplay between gravity, space-time, and the quantum world. The simplest black hole, the non-rotating, uncharged Schwarzschild black hole, is an object of perfect spherical symmetry. But the moment a black hole acquires spin, its character changes dramatically. A Kerr black hole, as it is called, is no longer a simple, static object. Its rotation drags the very fabric of space-time around with it. A phenomenon known as frame dragging. Near the event horizon, this effect is so powerful that it creates a region called the ergosphere, a place where nothing can stand still. Every object, every particle, every beam of light is forced to co-rotate with the black hole. This rotational energy can, in principle, be extracted, a process known as the Penrose process. A particle can enter the ergosphere, split into two, with one piece falling into the black hole and the other escaping with more energy than the original particle had. A spinning black hole can act as a colossal cosmic flywheel, a vast reservoir of rotational energy that can be tapped to power some of the most energetic phenomena in the universe, like the relativistic jets of quasars. The quantum world adds another layer of complexity and wonder. The process of superradiance suggests that a spinning black hole can spontaneously amplify certain quantum fields, creating a black hole bomb that would release its energy in a massive burst. The interaction between the spin of the black hole and the quantum fluctuations of the vacuum is a rich and largely unexplored area of theoretical physics. The addition of electric charge creates a Reissner-Nordstrom black hole, an object with both a gravitational and an electric field. The interplay between these two fundamental forces creates a complex and fascinating structure, with both an outer and an inner event horizon. Classically, it would be possible to travel through the outer horizon and avoid the central singularity, potentially passing through a wormhole into another region of space-time, or even another universe. However, it is thought that these inner horizons are fundamentally unstable, and that any small perturbation would cause them to collapse into a singularity. The quantum effects in a charged black hole are also intriguing. The strong electric field near the event horizon could spontaneously create real electron-positron pairs from the vacuum, a process known as the Schwinger effect, which would act to neutralize the black hole's charge. The study of these more exotic black holes is not just a mathematical exercise. It is a way of probing the deep structure of our physical theories. The existence of solutions with naked singularities not hidden behind an event horizon in some of these models, has led to the formulation of the cosmic censorship conjecture, the idea that nature abhors a naked singularity, and that some, as yet undiscovered, principle of physics must prevent their formation. The world of higher dimensional black holes, predicted by string theory, is even stranger. A black hole in 5 dimensions is not a sphere, but a black ring, and in higher dimensions, a whole zoo of black brains, black strings, and other exotic topologies become possible. The study of these objects is providing deep insights into the mathematical structure of string theory and the nature of quantum gravity. And finally, the development of black hole analogs in the laboratory is allowing us to test some of these exotic ideas experimentally by creating systems in condensed matter physics, like a Bose-Einstein condensate or a flowing fluid, that mimic the properties of a black hole's event horizon. Scientists can study the analog of Hawking radiation and other quantum effects in a controlled laboratory setting. These are not real black holes, but they are governed by similar mathematical equations, and they provide a powerful tool for testing the conceptual framework of black hole thermodynamics and the quantum physics of curved spacetime. The study of black holes, in all their varied and wonderful forms, is one of the most exciting and dynamic frontiers in modern science. They are the ultimate cosmic laboratory, a place where the laws of nature are pushed to their absolute limits and where the deepest secrets of gravity, of space-time, and of the quantum universe are waiting to be revealed. The discovery of Hawking radiation in 1974 was a moment of profound and revolutionary insight, a theoretical breakthrough that forever changed our understanding of black holes and forged a deep and unexpected link between the disparate worlds of general relativity, quantum mechanics, and thermodynamics. Until that point, black holes were seen as the ultimate cosmic prisons, perfect absorbers that swallowed everything, including light, and from which nothing could ever escape. They were thought to be completely black, completely cold, and, in a sense, completely dead. Hawking's brilliant and subtle calculation turned this picture on its head. He showed that when the principles of quantum field theory are applied in the curved spacetime around a black hole, something remarkable happens. The quantum vacuum, which we now understand to be a seething sea of virtual particle-antiparticle pairs, is disturbed by the intense gravity near the event horizon. This can lead to a process where one member of a virtual pair falls into the black hole, while the other escapes to infinity. To an outside observer, it appears as if the black hole is emitting a steady stream of particles. The particle that fell in must have a negative energy to conserve the total energy of the system, which means that the black hole loses a tiny amount of its mass energy with each emitted particle. The black hole is not black, it radiates. And this radiation, the Hawking radiation, has a perfect thermal blackbody spectrum with a temperature that is inversely proportional to the black hole's mass. This means that smaller black holes are hotter and radiate more intensely than larger ones. For a macroscopic, stellar mass black hole, this temperature is incredibly, almost unmeasurably, low, a tiny fraction of a degree above absolute zero. But for a microscopic, primordial black hole, the temperature could be immense. This process of radiation means that black holes are not eternal. They evaporate. As a black hole radiates, it loses mass, which causes its temperature to increase, which in turn causes it to radiate even faster. This creates a runaway process that accelerates over time, culminating in a final, explosive burst of high-energy radiation as the black hole disappears completely. This discovery had a profound impact on the field of physics, as it provided the first concrete example of a physical process that requires a combination of all three of the great theories of the 20th century. It is a phenomenon that is fundamentally gravitational, fundamentally quantum, and fundamentally thermodynamic. This led to the development of the field of black hole thermodynamics, a beautiful and consistent mathematical framework that shows a deep and surprising analogy between the laws of black hole mechanics and the laws of classical thermodynamics. The first law of black hole mechanics, which relates changes in a black hole's mass to changes in its area, spin, and charge, is the direct analog of the first law of thermodynamics, the conservation of energy. The second law of black hole mechanics, Hawking's area theorem, which states that the surface area of a black hole's event horizon can never decrease in a classical process, is the analog of the second law of thermodynamics, the law of increasing entropy. In fact, the physicist Jacob Bekenstein had proposed, even before Hawking's discovery, that the area of a black hole's event horizon is a measure of its entropy, its hidden information content. Hawking's discovery of thermal radiation provided the missing piece of the puzzle, the temperature, which allowed for a complete and consistent thermodynamic description. The third law of thermodynamics, which states that it is impossible to reach absolute zero temperature, has its black hole analog in the statement that it is impossible to create a black hole with a zero surface gravity, an extremal black hole. The discovery of Hawking radiation was a moment of stunning unification, a glimpse of the deep and beautiful connections that lie at the heart of our physical theories. But it also, as we have seen, opened up a Pandora's box of new and profound puzzles, most notably the information paradox, a puzzle that has driven much of the progress in theoretical physics for the past 50 years, and one that continues to challenge and inspire us in our quest for a final, unified theory of everything. The black hole information paradox, born from the clash between Hawking's discovery of thermal radiation and the fundamental principles of quantum mechanics, is one of the deepest and most consequential puzzles in all of theoretical physics. It is a paradox that has forced us to question our most basic assumptions about the nature of information, of space-time, and of reality itself. The core of the paradox is a stark contradiction. Quantum mechanics, at its very foundation, is built on the principle of unitarity, the idea that information is never truly lost. The wave function of a closed system evolves in a perfectly deterministic and reversible way. If you know the state of the system at one time, you can, in principle, calculate its state at any other time, either in the future or in the past. Information is scrambled, not destroyed. General relativity, on the other hand, seems to tell a different story. The event horizon of a black hole is a one-way membrane. Information can fall in, but it can never get out. And when the black hole completely evaporates into a seemingly random thermal bath of Hawking radiation, the information about the matter that formed it appears to be gone forever, erased from the universe in a way that fundamentally violates the principle of unitarity. This is the paradox. For decades, this was a battle between the two giants of 20th century physics. On one side, you had the quantum purists, who insisted that unitarity must be preserved at all costs, even if it meant that our understanding of space-time and causality had to be radically altered. On the other side, you had the relativists, including, for a long time, Stephen Hawking himself, who argued that the information was truly and irretrievably lost, and that quantum mechanics would have to be modified to accommodate this new gravity-induced non-unitarity. The debate has been long, technical, and often acrimonious. But over the years, the consensus has slowly shifted in favor of information preservation. The theoretical evidence from string theory and the ADS-CFT correspondence has provided powerful, if indirect, arguments that the process of black hole evaporation must be unitary. This has led to a host of creative and often bizarre proposed solutions to the paradox. One of the earliest ideas was that of black hole remnants. Perhaps the black hole does not evaporate completely. Perhaps it leaves behind a tiny, stable, Planck mass relic that contains all the information that fell in. This would preserve unitarity. But it comes with its own set of problems. An infinite amount of information would have to be stored in a tiny, finite object, and the universe would be filled with these otherwise undetectable relics, which would have profound cosmological consequences. Another, more mainstream, idea is that the information is not lost, but is subtly encoded in the outgoing Hawking radiation. The radiation is not perfectly thermal, but contains tiny, almost imperceptible quantum correlations that carry the information about the black hole's history. This is the most conservative and, for many, the most plausible solution. The problem is that it is incredibly difficult to show how this information encoding would work in detail. It seems to require a form of spooky, non-local interaction at the event horizon, a violation of the classical, local picture of space-time. This has led to some of the most radical and controversial ideas in modern physics. The concept of black hole complementarity, proposed by Leonard Susskind and others, suggests that the information is both inside the black hole and outside, encoded in the radiation, but that no single observer can ever see both at the same time, thus avoiding a logical contradiction. More recently, the firewall paradox, posed by a group of physicists in 2012, has argued that the assumptions of complementarity are inconsistent, and that an observer falling into an old black hole would be incinerated by a firewall of high-energy particles at the event horizon. This would preserve unitarity, but at the cost of violating one of the most cherished principles of general relativity, the equivalence principle, which states that the laws of physics should be the same for all observers, including one in free fall. The information paradox is still far from being resolved. It is a deep and complex problem that touches on the very foundations of our understanding of the universe, but it is also a powerful and productive one. It has been a crucible for new ideas, a testing ground for our theories of quantum gravity, and a constant reminder that the universe, at its most fundamental level, is far stranger, more subtle, and more beautifully interconnected than our classical intuition can ever hope to comprehend. The answer, when it finally comes, will likely involve a radical rethinking of our concepts of space-time, of locality, and of information itself. The strange and wonderful phenomenon of quantum entanglement, the spooky action at a distance that so vexed Einstein, has, in recent years, emerged as a central and surprisingly powerful player in the ongoing drama of the black hole information paradox. It is an idea that suggests that the deep, non-local connections of the quantum world may be the key to understanding the deep, gravitational mysteries of black holes. The connection is a natural one. The process of Hawking radiation itself is fundamentally an entanglement phenomenon. The virtual particle-antiparticle pair created at the event horizon is an entangled system. When one particle falls in and the other escapes, the escaping particle remains entangled with its partner inside the black hole. As the black hole continues to radiate, it becomes more and more entangled with the radiation that it has emitted. This is the source of the information paradox. The principle of monogamy of entanglement in quantum mechanics states that a quantum system can only be maximally entangled with one other system at a time. The outgoing Hawking radiation particle is already maximally entangled with its partner inside the black hole. But for the information to get out, it must also become entangled with the radiation that was emitted earlier. This is a quantum impossibility, a logical contradiction that lies at the heart of the firewall paradox. This has led to a revolutionary and beautiful idea, the ER-EPR conjecture. This conjecture, proposed by physicists Juan Maldacena and Leonard Susskind, suggests a deep and unexpected equivalence between two of Einstein's most famous and seemingly unrelated ideas. EPR refers to the Einstein-Podolsky-Rosen paradox, the thought experiment that first highlighted the strange, non-local nature of quantum entanglement. ER refers to the Einstein-Rosen bridge, the original name for what we now call a wormhole, a theoretical tunnel through spacetime that could connect two distant points. The ER-EPR conjecture proposes that these two concepts are, in fact, two different descriptions of the same, underlying physical reality. A pair of entangled particles is, in a deep, geometrical sense, connected by a wormhole. The spooky, non-local correlation of entanglement is the quantum manifestation of this hidden geometrical connection. This is a staggering idea, one that weaves together the fundamental principles of quantum mechanics and general relativity in a new and profound way. It suggests that the very fabric of spacetime may be emergent from the web of quantum entanglement, and it has profound implications for the information paradox. In the ER-EPR picture, the inside of the black hole is not a separate, causally disconnected region. It is geometrically connected to the outgoing Hawking radiation via a vast and complex network of microscopic wormholes. The information is not trapped inside, it is non-locally present in the radiation outside. Through these entangled wormhole connections, the interior of the black hole is, in a sense, built from the same quantum degrees of freedom that make up the radiation. This is a concept that is deeply tied to the holographic principle. It provides a specific, dynamical mechanism for how the information in the three-dimensional bulk of the black hole can be encoded in the two-dimensional boundary of the outgoing radiation. It is a picture that is still being developed, and it is full of technical and conceptual challenges. But it is one of the most exciting and promising ideas in modern theoretical physics. It suggests that the solution to the information paradox will not be found in a small modification to our existing theories, but in a complete and radical rethinking of the relationship between quantum mechanics and the geometry of spacetime. It is a vision where the strange, non-local connections of the quantum world are not just a bizarre feature of reality, but are the very threads from which the fabric of spacetime itself is woven. Entanglement is not just a spooky action at a distance, it may be the very glue that holds the cosmos together. The cosmic stage is not just set by the familiar actors of matter and energy that we can see and touch. The vast majority of the universe's inventory, about 95% of its total mass energy content, is made up of two mysterious and invisible entities, dark matter and dark energy. And in a surprising and controversial new development, some scientists have proposed a deep and unexpected connection between these two great cosmic mysteries. A connection that is mediated by the universe's most enigmatic objects, black holes. Dark matter is the invisible scaffolding of the cosmos. It is a mysterious, non-luminous substance that does not interact with light, but whose gravitational influence we can see everywhere. It is what holds galaxies together, preventing them from flying apart. It is what shapes the large-scale structure of the universe, the vast cosmic web of filaments and voids. We know it is there, but we do not know what it is. It is likely a new, undiscovered type of fundamental particle, one that interacts only weakly with the particles of the standard model. Dark energy, as we have seen, is the even more mysterious force that is driving the accelerating expansion of the universe. It is a smooth, uniform energy that seems to be an intrinsic property of space itself, a form of cosmic anti-gravity. For a long time, these two dark components of the universe were thought to be completely separate and unrelated phenomena, but a recent and provocative theory has proposed a startling connection. The theory, developed by a team of astrophysicists, including Duncan Farah, suggests that black holes themselves could be the source of dark energy. This idea has its roots in a concept from the 1960s, which proposed that a hypothetical object made of pure vacuum energy would, from the outside, look and behave gravitationally just like a black hole. But instead of having a singularity at its center, it would be a smooth, non-singular object, its repulsive vacuum energy balanced by its own gravitational pull. The new theory takes this idea a step further. It proposes that black holes are not just made of collapsed matter, but are coupled to the expansion of the universe itself. They contain a core of vacuum energy, and as the universe expands, this vacuum energy core also grows, causing the mass of the black hole to increase over time. This is a radical idea. It means that the mass of a black hole is not just determined by what it eats, but also by the evolution of the cosmos as a whole. This is a testable prediction. If black holes are growing in this way, then the supermassive black holes at the centers of galaxies should be more massive relative to their host galaxies in the present-day universe than they were in the early universe. And this is exactly what the proponents of the theory claim to have found. By comparing the masses of supermassive black holes in distant, dormant, elliptical galaxies with those in nearby, similar galaxies, they found that the nearby black holes are significantly more massive by a factor of 7 to 20 than their distant counterparts. This suggests that the black holes have been growing over cosmic time, not by eating, but by cosmological coupling. This is a highly controversial result, and it is still being debated in the astronomical community. Many other astrophysicists argue that this apparent growth can be explained by other, more conventional, astrophysical processes, such as the selection bias in the samples of galaxies being studied, or the complex and not fully understood history of galactic mergers. But if the result holds up to further scrutiny, its implications would be profound. It would mean that dark energy is not a smooth, uniformly distributed field, but is localized within the hearts of black holes. It would provide a direct, physical source for the cosmic acceleration, and it would forge a deep and unexpected link between the two greatest mysteries of modern cosmology. It is an idea that is still in its infancy, and it faces many theoretical and observational challenges. For example, the total mass of all the black holes in the universe is still far too small to account for the observed amount of dark energy. But it is a beautiful and creative idea, one that is forcing us to rethink our most basic assumptions about the nature of black holes, of dark energy, and of the intricate and beautiful connections that bind our universe together. The study of black holes, in all their varied and wonderful forms, is one of the most vibrant and exciting frontiers in modern science. It is a field where the deepest questions of fundamental physics meet the most advanced observational technologies, a place where we can probe the very limits of our understanding of gravity, of space-time, and of the quantum universe. From the classical, macroscopic black holes born from the death of massive stars to the hypothetical, microscopic quantum black holes that could be created in our particle accelerators. These enigmatic objects are a rich and fertile ground for discovery. The classical view of a black hole as a simple, featureless object, described only by its mass, charge, and spin, has given way to a much more nuanced and complex quantum picture. We now understand that black holes have a temperature, an entropy, and that they radiate and evaporate over immense timescales. This has led to the profound information paradox, a puzzle that has been a driving force in theoretical physics for half a century and has led to some of our deepest insights into the nature of quantum gravity, including the holographic principle and the ERR-EPR conjecture. The study of the different flavors of black holes, the spinning Kerr black holes with their frame-dragging ergospheres, the charged Reissner-Nordstrom black holes with their complex, multi-horizon structure, the exotic, higher-dimensional black strings and black brains of string theory is constantly pushing the boundaries of our theoretical understanding and providing new windows into the mathematical structure of the universe. And the development of black hole analogs in the laboratory, systems that mimic the properties of event horizons in controlled, condensed matter settings, is allowing us to test some of the most fundamental predictions of black hole physics, like Hawking radiation. In an experimental setting for the very first time, the recent and highly speculative proposal that black holes could be the source of dark energy is a testament to the enduring power of these objects to inspire new and creative thinking. It is an idea that, while still unproven, has the potential to unify two of the greatest mysteries in cosmology and to fundamentally change our picture of the universe's evolution. The future of black hole research is bright. With a new generation of gravitational wave detectors, like LISA, we will be able to hear the mergers of supermassive black holes across the cosmos, providing an unprecedented probe of the dynamics of space-time in the strong field regime. With powerful new telescopes, like the James Webb Space Telescope and the Event Horizon Telescope, we will be able to see the environment around black holes with ever-increasing resolution, testing the predictions of general relativity and searching for the subtle signatures of new physics. And with more powerful particle accelerators, we may one day even create a microscopic black hole in the laboratory, opening up a direct experimental window into the world of quantum gravity and extra dimensions. Black holes are no longer just the stuff of science fiction. They are real, physical objects, and they are one of the most powerful tools we have in our ongoing quest to understand the deepest secrets of the universe. They are the ultimate cosmic laboratory, a place where the familiar laws of our world are pushed to their breaking point, and where the new, more profound, and more beautiful laws of a final, unified theory may be waiting to be discovered.